बाद में यूक्लिड ने उसको पेल नाम दिया, PELL, पेल्स इक्वेशन, जबकि वो ब्रह्मगुप्ता ने ऑलरेडी दिया हुआ था। तो बहुत सारी चीजें जो है ब्रह्मगुप्ता ने दी। और एक और मेन जो कंट्रीब्यूटर थे भास्कराचार्य, उन्होंने बहुत कुछ दिया इंडियन मैथमेटिक्स को 12th सेंचुरी में। और उन्होंने फर्स्ट टाइम कहा कि भाई देखो, एक जीरो और एक है, दो नंबर्स के बीच में भी इनफाइनाइट नंबर एग्जिस्ट करते हैं। भास्कराचार्य ने बहुत सारी चीजें बताई। ही इज ग्रेट कंट्रीब्यूटर ऑफ इंडियन मैथमेटिक्स। इसके बाद से ये मान लिया गया कि उसके बाद इंडियन मैथमेटिक्स का ऑरा खत्म हो गया है। केरला स्कूल ऑफ मैथमेटिक्स, और वहां पे बहुत काम हुआ उस पे। इनफाइनाइट सीरीज एक्सप्रेशन ऑफ साइन, कोसाइन, tan inverse, all those things were given by a great mathematician Madhav from Kerala school। और उसके बाद से बहुत सारे ट्रेडिशन हैं जो चल रहे हैं अभी तक। तो हमारा मैथमेटिक्स अभी तक जिंदा है, और हम लोग उम्मीद कर रहे हैं कि आप लोग बहुत कुछ आगे करेंगे। आप देख रहे हैं कि 2014 में मनोज भार्गवा ने फील्ड मेडल प्राप्त किया इंडियन ओरिजिन मैथमेटिक्स के। 2018 अच्छे बैंकिस्ट गॉट फील्ड मेडल। तो hopefully more are going to come from young mathematicians, and maybe some of you people we hope. So I think I will stop. The story is endless, so thank you.
Thank you so much, sir, for your kind and graceful words. We are always feel privileged to have your support and supervision. Now, in the next series, in the series of events for today's celebration, we have 4 participants in the speech competition and 1 short talk. Now, to keep this event more entertaining and lively, we have students for poems and singing competitions as well. Not competitions, singing performances as well. In order to acknowledge the hidden talents of students and to provide them an opportunity to embrace their skills, we have also organized poster making and rangoli making competition. There are 4 teams to compete in poster presentation and 3 for rangoli competition. It is a matter of great honor that Professor Ramakrishna Basurika is also here at this celebration. Thank you so much, sir, for your kind presence. I request him to please come over and share some insights with us. Sir, please.
Hello, good afternoon, everyone. So, first of all, I would like to really congratulate Professor Goldbach Conjecture. He gave an excellent account about ancient mathematics. So, I also learned a lot of things. So he has done a lot of homework, so I'm really impressed with that one. And then I would like to really congratulate all the faculty members of mathematics and statistics, because last 1 year I have been seeing that they have been organizing a lot of programs related to mathematics, and even some FDPs and all, where external outside people are involved. So it is a really good path they are going through it, and we have not seen this kind of visibility of this department in the past, but now I can see Professor Goldbach Conjecture and all other their faculty members, Dr. Sachin and others, they are leading in this particular matter. So it is good to see a lot of students here, okay, which was not there 1 year back or even 6 months back, right? So this is a very good event that we are organizing on National Mathematics Day. And especially about Shinyuasan Ramanujan. So in mathematics, if you see, there are only, you may know many mathematics, right, of repute, but only a few mathematicians are there that everybody knows outside mathematics, right? And one of them is Shinyuasan Ramanujan. You ask anybody outside mathematics, they know about him. Like he was talking about Aryabhatta. So these are a few names that everyone knows, and I think you all should also make mathematics more popular, okay, compared to other regions, other sciences and other subjects, because this will all depend on you, students, right? Who are doing MSc, who are doing PhD. So it is not just we are sitting in our shell and studying our masters or PhD, but also you need to popularize mathematics and statistics and make it more visible to other sciences. Of course, mathematics and especially statistics are the areas everybody uses, not only in sciences but even outside. Without that, we cannot do a lot of experimental validation. This is working or not working. So, from that viewpoint, it is very important. But you want more people to come into this stream. So that depends on the faculty and students. Like you want really good students, still better and better quality to come into masters and PhD. So it will depend on you how you popularize this area of science, that is mathematics and statistics. Okay. Okay. Thank you all, and I hope you have a really good event. I saw that you have many good programs like speech, poem, and these kind of events generally you don't see, right, associated with mathematics. So there is something really they are doing something, you are doing something different. Okay, thank you.
Thanks a lot, sir, for your precious words and for your guidance that was really needful. Now, without taking much of your time, kindly permit us to start the program. So, sir, can we begin the speeches now? Yeah. So we will start this event with some intellectual speeches. I would request all the speakers to please limit your speeches within 10 minutes. Okay. Let's begin the speech competition with Mr. Saurabh, who is the first contestant in this category. The title of the speech is "In the Shoes of Ramanujan." Let's call Saurabh to present his views and illuminate the audience with his words. Please give a big round of applause for him.
Good afternoon, all of you present here, our teachers, my classmates, and my name is Saurabh. Thank you for being here on this auspicious day, or should I call it Ramanujan's 134th birthday. I'm here to deliver a talk over a topic in the shoes of Ramanujan. So basically, who was Ramanujan? We all know him as the man who invented this is how I got to know him, through a film, who was titled The Man Who Infinity. So I'm here to take you on a venture, this journey to understand it better. And let's begin. As you all might know that he was devout Brahmin, and at a superstition level, it was not allowed for Brahmins to travel overseas. It was not allowed. So basically, he had his beliefs, and he had to choose between his beliefs and the subject truly loved, which was mathematics. So he was struggling with a dilemma, and he had to choose between the beliefs and the mathematics, and we all know that what he chose. But most important thing that people don't ask is, why did he do that? How could he put his beliefs over a subject? Personally, I don't think that mathematics was merely a subject for him, and he saw beyond numbers, patterns, and logics. How he would have struggled these nights when he got the reply from Hardy. Dear Hardy, not Hardy Salon. In our times, maybe in the near future, we all will be having those same nights, struggling over what we have to do, because more or less our MSc will be over in about what, 8 months. So maybe our nights will be as hard as Ramanujan's, or maybe harder. What we can do is take inspiration from him, and which was to dedicate his life to his work. He did, and we all understood how he became such a well-known, renowned mathematician, and we are proud to have him as an Indian. He prayed to his Namagiri, his goddess Namagiri. He saw her in his work. He never took a lead from his work because all he wanted to do was pray to his Namagiri by his mathematics, even when he was suffering from tuberculosis. Now, friends, isn't this some call to believe on God, to dedication to His work? Maybe this is called bhakti. There he was, and I quote, he said that, and I quote, an equation has no meaning to me unless it expresses thought of God. This dedication took him from, metaphorically speaking, the realm of the stupid to the exploration of the mathematics. Well, we are all in this exploration together. We are learning mathematics, and what I wanted to do is to give you some questions to think about, which is why is mathematics? How does it develop? And maybe one day you might ask, what itself is mathematics? So I believe we all have been called quote unquote mathematical genius by someone. That's why we took this course. We thought that this course would be better for us. But this was the hype of the comment that we made, and it turns out we are here. So don't worry about it, and I wish you very, very good luck for these things. And I'll give you these questions. Build on these questions and really understand that what you truly are, what you truly believe in, and why. Because these are the questions that he might have asked to himself. Why he wanted to leave India, why he wanted to cross the seas when it was forbidden for him. He did, he come back and stayed. He died here, did his mathematics. Explore yourself, your subject and your surrounding, especially your options. We may never be able to understand that what would it be like to be in his shoes. But possibly, we could see those shoes. We can explore and expand towards what we are from here and where we are going. This is where I'd like to end my talk, leaving you with a question. What is mathematics if not the language book spoken by the universe, translated by the stars, and understood with logic? Thank you all for your time. I wish you a good life. Take care. May God go with you.
Thank you so much, sir. That was really remarkable speech.
In order to continue our speech competition, our next contestant, Mr. Shivan Pal, is ready with his interesting talk. Now, please invite him on the stage with a huge round of applause.
Good afternoon to all my teachers and my fellow classmates and PhD scholars. Today, before I begin, I want to put forward an interesting possibility. And for that, I want all of you, all the teachers and students, to take a deep breath in and hold it for me. Take a deep breath in and hold it. Okay, you can let it go now. It is a likely possibility that right now you are breathing the molecules that once were breathed out by Ramanujan when he thought the formula for the total number of partitions of natural numbers. Why is that true? It is true because every time you take a breath, you inhale more molecules of air than there are breaths of air in the entire atmosphere of Earth. So when you are sitting there and not getting anything done, you may think and wonder that at least I am sharing the same molecules with any mathematician in the history, possibly Ramanujan. So now today, on this occasion of Mathematics Day, which is 134th birth anniversary of the great Indian mathematician Shinyuasan Ramanujan, I want to convey some of my thoughts on a topic that is hardly ever discussed in any school or college. I tried to find hard, but I didn't find any school or college where this topic is discussed. The topic is the value of mathematics. And why is it really important to know it? Well, as you have guessed that we all study mathematics. Might be possible that it might come as a surprise for some of you. Well, moving on. So, what is really so important about mathematics? In my opinion, if you ask me, mathematics is one of the most misunderstood subjects in the general public. If you ask, then most of the people would say that it is dull, boring, it is all about numbers and computation, and some of you would say, "Hi, dull लगता है मैथ्स मैंने तो छोड़ दी." We label mathematics separately as pure and applied, as though the pure mathematics is completely useless. As a passionate student of science and mathematics, I beg to differ. Mathematics is not about only calculation. It is about logic. It is about reasoning. It is about trying to understand the operations of nature on their deepest level. It is also about trying to understand the things which are at the border of what is known and what is unknown. And it might happen sometime that those things may also seem too abstract, then one might say, this is completely useless. There can never be an application in the real world. On the contrary, I would say, your life as you live today in 21st century has its root in mathematics. Let me make my point through certain examples. We all have smartphones. I don't think there is anyone in this room who doesn't have a smartphone. A smartphone uses GPS, Global Positioning System. It consists of 31 satellites, and each of those satellites has a very accurate clock. They're called atomic clock. These clocks are really, really accurate, but still, up there in the orbit, these clocks run a bit faster. You might ask, why? Primarily not because of some technical error, but because the time itself runs faster up there in the orbit. And the difference is about 40 microseconds. Take into account several uses for hours. Suppose you are driving to other city and you are late. You are 11 kilometers away from your destination. Your mobile is showing that you are at your destination. So satellites must have to correct this. They have to calculate how much they have to slow it down before sending the data to your phones in order to compensate with our time. But how do we know about this fact related to the rate of flow of time? Because of the Einstein's theory of relativity. Now let's ask the question. What were the tools that he or other mathematicians used to develop that theory? Mathematics. And if you let me be precise, I would say Riemannian mathematics, Riemannian geometry, which is the parent of the theory of relativity. And it is too abstract at first sight to have any use in the real world, but apparently it has. Take another example. It's 1969. People are eagerly waiting for an announcement. Apollo 11 landed on our moon and Neil Armstrong said, and I quote, "There's one small step for man, one giant leap for mankind." How did that happen? What did we use that make us able to leave Earth and travel 300,000 kilometers and land on the moon? Newtonian physics, which uses the integral and differential calculus that most of us struggle to understand, to comprehend in 12th class. And Isaac Newton invented it just to solve a problem related to the orbits of planet. And after that, he turned 26. Not only that, by the 18th century, calculus was established as pure mathematics. And as a pure mathematical theory, calculus has many more applications than initial application of Newton. Take one more. We all do online shopping, booking, banking, etc. Your valuable money is safe while making transaction. How? Number theory. And in past, number theory has been considered as a feeble mathematics. Many years later, what we did? We used the same mathematics to design the computer security system. And if we observe closely, the number theory is actually completely pure mathematics. All the big companies like Google, Facebook, Amazon, Twitter, Flipkart, etc., completely rely on the sophisticated algorithms developed using the mathematics that is usually considered as useless. There are many more examples of group theory, ring theory, field theory, algebraic topology, algebraic geometry, etc. It would take me hours to tell you all the applications. There are so many applications in quantum physics. LED lights works because of quantum physics, and entire quantum physics is based on mathematics. So at last, the message that I want to convey is that mathematics is like a pyramid, on the top of which there are immediate applications of mathematics to our everyday life. But without a wide and strong base, the pyramid cannot be so high. Topics like mathematical logic and set theory may not have immediate application in the real world, but they are required in order to develop the tools which in turn fulfill your needs. It enables us to solve the challenges that a lot of us thought at the time that they could not be solved. So let us remember and respect the powerful subject, I might say the language of the universe, and the people who work on it for their entire life and understand what mathematics is, how and why it works, and let it be what it can be in serving the entire civilization. Thank you very much for listening and have patience.
Thank you so much, Shivam, for recalling the importance of mathematics.
As Alfonso de Martin once said, music is the literature of the heart. It commences where the speech ends.
Oh, music, I think my heartbeats have already gone up, and everyone here is eager to sink into the depth of music and joy.
So let's invite Miss Jaspreet for the singing performance.
सत श्री अकाल, नमस्ते, गुड आफ्टरनून। सबसे पहले मैं आप सभी को नेशनल मैथमेटिक्स डे पे बधाइयां देना चाहती हूँ। मैं जसप्रीत कौर आज आपके सामने एक सॉन्ग परफॉर्म करूंगी। आई होप यू विल एंजॉय इट। धुंधला जाए जो मंजिले, एक पल को तू नजर झुक जाए सर जहां वही मिलता है रब का रास्ता। तेरी किस्मत तू बदल दे, रख हिम्मत बस चल दे। तेरे साथी ये मेरे कदमों के है निशान। तू न जाने आस पास है खुदा, तू न जाने आस पास है खुदा। तू न जाने आस पास है खुदा, तू न जाने आस पास है खुदा। खुद पे डाल तू नजर, हालातों से हार कर कहाँ चला रे। हाथ की लकीर को मोड़ता मरोड़ता है हौसला रे। खुद तेरे ख्वाब के रंग में तू अपने जहां को भी रंग दे, कि चलता हूँ मैं तेरे संग में। हो शाम भी तो क्या जब होगा अंधेरा, तब पाएगा दर मेरा। उस दर पे फिर होगी तेरी सुबह। तू न जाने आस पास है खुदा, तू न जाने आस पास है खुदा। तू न जाने आस पास है खुदा, तू न जाने आस पास है खुदा। थैंक यू वेरी मच।
Thank you, Jaspreet. That was indeed a splendid performance. Everyone, please thank her for brightening the event.
Now resuming the speech competition, next in line is Mr. Satya Swaroop. He is going to put in the picture a gift less appreciated. All are requested to please welcome him on the stage with a huge round of applause.
Mathematics seems very similar to life, and you are more like this piece of paper. You see, life has its own way. It tears you down, crushes you, and probably throws you in the trash can. My dear guests, and all of the people who are present here, a warm welcome to each and every single one of you. I still remember as a kid, I had my first encounter with the age-old Pythagoras theorem. And it was introduced by none other than my beloved father. Raise your hand if you've ever had a strict father. Anybody? I can see a few hands. Don't be shy, come on, nobody's watching you. You combine all of them, all of that strictness, you get my father. Well, I'm just joking around. I'm very fortunate to have very supportive parents. When my father looks at me, and he says, son, you have an exam tomorrow, a math exam that. No else. You haven't studied anything till now. No problem. We will get through this together. And I'm looking at him as if he's a Superman or something. He has some magic wand or something, and he's gonna put a spell on me and I'm just gonna top the exam without actually studying anything. But then again, he starts and says, in a right triangle, hypotenuse square equals perpendicular square plus base square. And I look at him and ask, but Dad, there are no boxes in this formula. What squares are you talking about? He gives me that look and says, don't be silly, Satya. Fast forward to my first year in college. Well, kind of. My first year in UG college, there is this newly appointed guest faculty in mathematics. And she's taking a course in, well, the infamous real analysis. I've always used to get questions, but she never used to answer. One fine day, she starts teaching arithmetic of transfinite numbers. And then she starts talking about alpha naught and continuum and so on and so forth. To which I ask, but why do we need more numbers? We already have enough, and if all of them are the entire class is staring at me just like you guys are, as if I've taken a lot of money from them and I owe them back. Our HOD calls me, not you, sir, to visit her immediately in the office. I rushed there, explained her all the drama, and she gave me that look and said, don't be silly, Satya. Disappointed me. Went to my best friend at the time. I hold her hand and ask her, I'm so dumb and clumsy. Despite of all this, why do you still like me? She gives me that look and says, don't be silly, Satya. When she starts teaching me all of a sudden, every single day, and finally, when she states the marvelous Cantor's theorem, that is when I finally start connecting all the dots. Okay, from a set to its power set, a mapping can never be subjective. That means there has to be strict inequality, and bam, that's my eureka moment. You see, mathematics is more like a gift that keeps on giving, if and only if one can resist that odd hiccup here and there. And for following this subject rather religiously, events like the National Mathematics Day is more of a festival. When one opts to study mathematics, they don't just choose a mere subject. When one opts for this subject, they actually choose a way of living, a lifestyle, if you will. And who better to represent this lifestyle than the maestro of numbers himself, Sri Shinyuasan Ramanujan, I would like to take this opportunity to pay my homage to him and his legendary legacy, although I'm not entirely sure whether I am worthy enough to even take his name at all. His work, be it in number theory or in infinite series, are still relevant and paramount to this very day, which shows the degree of intellectual depth he possessed. And just like that, the man who knew infinity survived through the early struggles of his life to reap the gift called mathematics. So can you. You too can transform yourself from a mere piece of paper with a fair amount of fold to a very special and unique structure with the gift less appreciated, known as mathematics. Thank you so much for your presence here. I really appreciate the support. Thank you.
That was really an extraordinary talk. Thanks a lot, Satya. Audience, please admire participant hard work by putting your hands together. Next, in order to suit the ambience, Miss Manoma is coming with her own writing some poetries. So kindly welcome her with some more claps. Miss Manoma.
हेलो नमस्कार नमस्कार मेरा नाम मनोरमा पांडे है मैं अपनी स्वरचित कविता लेकर प्रस्तुत हूँ मेरी पहली कविता का शीर्षक है कर्ण इस कविता की भूमिका में है कर्ण और उसका जीवन कर्ण महाभारत का अत्यंत लोकप्रिय किरदार है उसका जीवन संघर्ष और चुनौतियों से भरा हुआ है महाभारत के किरदार कर्ण में तमाम अच्छाइयां हैं लेकिन साथ ही उसके चरित्र के कुछ दुर्बल पक्ष भी हैं जिनको मैंने शब्द देने की कोशिश की है सुनिएगा कुंती के बालपन की नादानी से उसने जीवन पाया था कुंती के बालपन की नादानी से उसने जीवन पाया था राजवंश का होकर भी सूतपुत्र कहलाया था मां ने उसे संदूक में बनकर नदी में बहाया था उसके जीवन पर प्रश्न चिन्ह लगाया था एक सूप में उसको पाला इसलिए सूतपुत्र कहलाया वो देने में किसी को निराश नहीं किया इसलिए दानवीर कहलाया वो भरी सभा ने जब उसके कुल पर प्रश्न दाग दिया तब दुर्योधन ने उसका हाथ थाम लिया होकर दुर्योधन के इस उपकार से उपकृत उसने मन मस्तिष्क की तारों को मित्रता से कर दी झुकृत दुर्योधन ने उसे अंग देश का राजा बनाया कर्ण ने उपकार व्यस्त ही लौटाया जब स्वयंवर में द्रौपदी ने किया उसका अपमान भूल गया वो अपना सारा ज्ञान जब युधिष्ठिर जुए में हार गए द्रौपदी को उसने निर्लज्जता की सीमा पार की अपनी सारी अच्छाई शर्मसार की जब कुंती मांगने आई अपने पुत्रों की जान की भीख तब उसने पूछा क्यों मिल रही उसे अब सीख वो कहाँ थी जब दुनिया ने उसे धिक्कारा था उस दानी ने प्रतिज्ञा की वो अर्जुन को छोड़कर किसी पांडव को नहीं मारेगा या तो वो अर्जुन को मारेगा या अर्जुन उसे मारेगा दूसरी कविता का शीर्षक है राधा कृष्ण भारतीय संस्कृति में राधा कृष्ण पूज्य हैं उनके दिव्य प्रेम पर काफी कुछ लिखा हुआ है कृष्ण के जीवन में कर्तव्य की पुकार आने से उपजी विरह की स्थिति में राधा की मनोस्थिति कैसे रही होगी कैसे भाव रहे होंगे मैंने उन भावों को शब्दों में ढालने का प्रयास किया सुनिएगा कृष्णा का ताल राग राधा का मन बाग हाथों में हो बंसी, माथे पर हो मोर पंखी, ग्वाले का भेष है, ब्रज का ये देश है। गाय है चराने को, माखन है खाने को, नैनों से होते हुए बातें थी, सुहानी वे रातें थी। बचपन का खेल था, राधा संग मेल था, अब बिछड़ने की बेला थी, अब बिछड़ने की बेला थी, कर्तव्य की पुकार थी। राधा की अखियों से बह चली अश्रुधारा और रोया ब्रिज सारा। अब हो ना हो ये मिलन, अब हो ना हो ये मिलन, राधा के माथे पर थी शिकन। कृष्ण ने राधा को समझाया, समय मुस्काया, कैसी है लीला भगवान की, कर्तव्य है आन बान शान की। समय का रथ आगे बढ़ चला, समय का रथ आगे बढ़ चला, भावुकता से रूल गया ब्रजवासियों का गला। फिर कभी ना हो सका ये मिलन, फिर कभी ना हो सका ये मिलन, पर राधा कृष्ण की ये कहानी, पर राधा कृष्ण की ये कहानी, राधा थी कृष्ण की दीवानी। कृष्ण का प्रेम अनोखा था, जिसका ना कोई सरीखा था। युग युग धरती गाती है, युग युग धरती गाती है, निस्वार्थ प्रेम की मिसाल सुनती। मेरी तीसरी कविता का शीर्षक है प्रकृति और जीवन। इस कविता में मैंने प्रकृति के माध्यम से जीवन को देखने की कोशिश की है। सुनिएगा। आसमान में टिमटिम करते तारों को देखा, आसमान में टिमटिम करते तारों को देखा, अंधेरे में जगमगाते दीपों को देखा। सूरज को उगते चढ़ते ढलते देखा, सूरज को उगते चढ़ते ढलते देखा, जीवन का परिवर्तन देखा। आसमान में छटा बिखेरता चांद, जैसे हो जीवन में सुख की छाया। गाती लहराती पत्तियां देखी, गाती लहराती पत्तियां देखी, जीवन की हंसी ठिठोली। महकते कुसुमों को देखा, महकते कुसुमों को देखा, जीवन का यौवन देखा। उन्मुक्त आकाश में खुशी का गीत गाती चिड़िया देखी, जीवन में स्वतंत्रता की अहमियत देखी। सोने के पिंजरे में बंद पक्षी का रुदन देखा, स्वतंत्रता का दुख और व्यक्तित्व का दमन देखा।
That was indeed a beautiful piece of poetry penned by us. Seema, isn't it wonderful to see that mathematics people are so creative at writing also? Yeah, of course, that's the beauty of mathematics people, that they can slay in all sorts of disciplines. A big thanks to the poet of mathematics department, Miss Manorama. Put your hands together to encourage her for more writing. Now, in the series of this speech competition, our last contestant is Miss Hamandeep Kaur. So I call Miss Haman, and she is going to introduce us with golden ratio. Please give a big round of applause to her.
Good afternoon to all present. Today we are celebrating National Mathematics Day, and we know the heart of all mathematics are numbers. So how can this occasion be complete without discussing about numbers? So on this special occasion, I'm going to introduce you all with a very interesting number, which is called as the golden number or the golden ratio. I see a certain order in the universe, and mass is one way of making it visible. This is a famous quote by American poet and novelist May Sarton. Indeed, this is true, and golden ratio is the one way to make that order visible. As usual, Sir says shortly. The contents include introduction about the golden ratio, a historical background, and its connection with the Fibonacci sequence, golden ratio in nature, human anatomy, geometry, architecture, anthropomorphism, golden ratio in logo design, and finally the conclusion and references. In everyday life, we use the word proportion either for the comparative relation between different parts of the things or for qualitatively to describe a harmonious relationship between different parts. In mathematics, proportion is used to describe equality of the type as 9:3, 5:7, and so on. As we shall see, golden ratio provides us with an intermingling of the two definitions. While defined mathematically, it is claimed to have pleasantly harmonious qualities. The golden ratio is a mathematical ratio with special properties and aesthetic significance. If someone asks you that what is the one thing common in mathematics, arts, geometry, beauty, design, life, solar system, and even the universe, then golden ratio is probably the best suited answer for this. Let's begin the ongoing journey of discovery with a basic understanding of this interesting number. The first very clear definition of what later became to be known as golden ratio was given around 300 BC by the founder of geometry, Euclid of Alexandria. Euclid defined a proportion derived from a simple division of a line into what is called as extreme and mean ratio. In Euclid words, a line is said to have been cut in an extreme and mean ratio when as the whole line is to the greater segment, so is the greater to the lesser. As you can see in the line segment AB, that line segment AB is said to be cut in extreme and mean ratio as when the length of the segment AC to ratio of the length AC to that of CD is same as that of the length of the whole segment, that is AB, to the longer part, that is AC. Here is a formal definition. Two quantities, they are said to be in golden ratio if the ratio of the sum of the quantities to the larger quantity, that is equal to the ratio of the larger quantity to the smaller quantity. As you can see in the diagram, A and B are the quantities. A is the larger one and B being the smaller one. If the ratio A to B is equal to A plus B to A, then this line will be said to be cut into golden ratio. We can express this figure algebraically as A plus B by A is equal to A by A, and we can denote it by 5. And on solving this equation, we will get a quadratic equation in 5, which on further solving, we will get one positive solution in the set of irrational numbers. And finally, we get the value, which is 1 plus root 5 by 2, which is the golden number we are talking about. And in decimal system, it is equivalent to 1.618033 and so on. For simplicity, we will use it up to 3 decimal places, like 1.618. Next are the symbol for the golden ratio. In professional mathematical literature, the common symbol for the golden ratio is the Greek letter tau. However, at the beginning of the 20th century, American mathematician Mark Barr gave the ratio the name phi. Here, the uppercase phi is used for the golden number, which is 1.618, and the lowercase phi that is used for the reciprocal of the golden number, and its value is 0.618. It is interesting to note that golden number is the only number whose reciprocal is 1 less than the original number, and also it is the only number whose square is 1 more than the original number. In today's world, we know it as golden ratio, but in recent times there were other names also. It was also called as golden cut, golden mean, golden number, golden fraction, medial fraction, extreme and mean ratio. And in more recent times, it was also regarded as divine, so called as divine quotient. Next, we are having Fibonacci sequence and golden ratio. Leonardo Fibonacci discovered a sequence that converges on phi. The Fibonacci sequence, what is it? Let's check. The Fibonacci sequence is made up of the numbers that are all addition of the previous two numbers in the sequence. It starts with the numbers 0 and 1, and after that it continues with the addition of the previous two terms. Like the third number will be 0 plus 1, 1, and the fourth one will be 1 plus 1, 2, and so on, 2 plus 1, 3, and it continues. The numbers in the Fibonacci sequence, these are known as Fibonacci numbers. These are denoted by Fn, and the sequence can be represented as Fn is equal to Fn minus 1 plus Fn minus 2. That is the sum of the previous two terms. And what is so interesting about this Fibonacci sequence? How is it related to golden ratio? Let's see. The interesting aspect of the series is that after the first 4 or 5 numbers, if each number is divided by its immediate predecessor, it yields a value closer to the golden number, which is 1.618. And this value approach is closer and closer as the golden ratio to the golden ratio as the series progresses. The elucidation of the relationship between golden section and the Fibonacci sequence plays a vital role to detect and identify the presentation of this particular ratio in nature. Here in the image, this spiral is known as the Fibonacci spiral. Basically, the building blocks of this spiral are the squares, whose dimensions are the same as the numbers in the Fibonacci sequence. As you can see, the smaller one is 1 of side length 1, 1, and then 2, 3, and 5 as the numbers are there in the Fibonacci sequence. So it is known as the Fibonacci spiral, which can be seen in most of the things as you will see in the following slides. Next, the golden ratio in nature. There are many fascinating mathematical relationships between phi and the Fibonacci sequence. Let's have a look at how phi and the Fibonacci sequence manifest themselves in nature. The first example here, I have shown the flowers. In almost all the flowering plants, the number of petals on the flower is a Fibonacci sequence. The golden ratio is seen in this flower as in terms of petal arrangements. The top view of the flower represents a Fibonacci spiral. The ratio of the petals between each layer, that is the golden ratio. Next, another beautiful example is the seed heads. Spiraling patterns of the seed heads, as seen in case of sunflowers, are a great example of Fibonacci sequence and the divine ratio. In seed heads, new seeds are formed at the center and they migrate outward in radial fashion as they grow older. Since each whirl of the seed follows a sequence, that is the Fibonacci sequence, and the ratio of any adjacent whirls, that is the golden ratio. As you can see here, the number of seeds are shown by red and blue. They are also the numbers in the Fibonacci sequence. Another example is of pine cone. Pine cone are also arranged in a Fibonacci spiral. The ratio between the number of pods in successive whirls, that is the golden ratio. Fruits and vegetables, they are also related to the golden ratio. The same pattern is observed in case of fractals like fruits, vegetables. The most common examples are pineapple, red cabbage, banana, cauliflower, and so on. Trees. When the main trunk of a tree branches out, it gives rise to a side branch, which will further go on to divide and produce two or more branches. At each branching node, the ratio of the new branches to the old, that is the golden ratio. And shells, snails, seashells, they also exhibit Fibonacci spiral, and each chamber of the Nautilus, when compared to its immediate successor, reveals the golden ratio. Also, the galaxies, the Fibonacci spiral is also observed in case of spiral galaxies. Our own galaxy Milky Way is one such celestial entity. Hurricanes. Hurricanes also involve the Fibonacci spiral pattern, revealing the golden ratio. These were the examples for the golden ratio, relation of the golden ratio with nature. Now, next comes the human anatomy. As you can see your face here, there is a saying that beauty lies in the eyes of the beholder. But there is an evidence that the facial aspects of the beauty in man and woman, that is related to the golden ratio. The more the dimensions of the proportions are closer to the golden ratio, the more beautiful and attractive the person looks. It is one of the parameters to. It is one of the parameters that is used to find the most beautiful person, as you can see on Google also. In human face, you can see here some of the proportions are listed. In the first image, inside of the eyes to the face width, this ratio is nearly similar to the golden ratio. In the second image, the side of face to the inside of the near eye to the opposite side of the face. This ratio is also closer to the golden ratio. In the third image, you can see the pupils to the lip center line to the chin. This is also closer to the golden ratio. The more it will be closer to the golden ratio, the more attractive and beautiful the face will look. Next, golden ratio is also present in the human hand. Our fingers that have three sections. The proportion of the first two to the full length of the finger, that gives the golden ratio. The proportion of the middle finger to the little finger, that is also an example of a golden ratio. Human brain, for beta rhythm, which corresponds to the mental activity, the ratio of its frequency bands, it also coincides with the golden proportion. DNA molecule, the program for all life, it is also based on golden section. It measures 34 angstrom long by 21 angstrom wide for each cycle of its double helix with spiral, which are the numbers in the Fibonacci series, as we can already see, and their ratio is nearly closer to the golden ratio. So you can see golden ratio is everywhere in nature and also in human anatomy. But this is not the end, there are much more to this. Geometry and architecture. Throughout history, the relation between mathematics and nature has had an influence on architecture. This is the Parthenon. The Parthenon in Athens, built by the ancient Greeks from 447 to 438 BC, is regarded by many to illustrate the presence of golden ratio in design. As you can see from here, a closer look of the Parthenon, there are various dimensions in this design that are closer to the golden ratio. As the structural beam on the top of the columns is in a golden ratio proportion to the height of the columns. Similarly, the structural beam on the top of the columns has a horizontal dividing line that is in golden ratio proportion to the height of the supporting beam. Next, Taj Mahal, you all know. So this is one of the finest example of the architecture. Taj Mahal is considered as one of the finest example of architecture, and in the making of the Taj Mahal, golden ratio was also included. As you can see from the closer view, there are many proportions of the building design that are in golden proportion or the golden ratio. Next is St. Paul's Cathedral, situated in London. This building is also comprises of the golden proportion in its design. Next is the Toronto CN Tower. The CN Tower in Toronto, the tallest tower and the freestanding structure in the world, contains the golden ratio in its design. The ratio of the observation deck at 342 meters to the total height of the tower is 0.618, which is the reciprocal of phi, which we denote by the lowercase phi. So that was all about geometry and architecture. There are many more examples related to this, but due to shortage of time, I had included only a few. Anthropomorphism. It is making non-human things look human. Anthropomorphism is the attribution of human traits, emotions, or intentions to the non-human entities, as you can see in the animation movies and in the cartoons. Here, also golden ratio play a vital role. See how many of you have seen the movie Cars, the animated movie? Yeah, many of you have already seen. So you can easily recognize these star factors. So in the animators of the Disney picture, they use golden proportion to make the cars look like humans. This is called the anthropomorphism. They place the eyes on the windshields and the mouth on the golden ratio point between the eyes and the bottom of the car's face. And this proportion, as you can see from the image also, it resembles to the human face. Next, golden ratio in logo designs. Many designers use the golden proportion to make their designs look more symmetric and beautiful. I have listed some of the logo designs here, which are based on the golden ratio. And finally, the conclusion. As you can see, the golden ratio has inspired the thinkers of all disciplines like no other number in the history of mathematics. And not everything is based on the golden ratio, but the number of places in which it seems to appear is truly amazing. And we are sure to uncover it more and more as technology advances and our knowledge of the physical universe expands. Here are some of the references. Thank you so much for your patience.
Thank you so much, Aman. That was really a remarkable speech containing lots of examples. Let's clap together to encourage us. Now, next to cheer the surroundings, I call Ms. Timothy for another song performance. Please give a big round of applause for her.
Good afternoon, everyone present here. I'm Simran and I'm going to sing a song. Gina is in Kannada. Hope you all will enjoy it. किसी की मुस्कुराहटों पे हो निसार, किसी का दर्द मिल सके तो ले उधार, किसी के वास्ते हो तेरे दिल में प्यार, जीना इसी का नाम है।
किसी की मुस्कुराहटों पे हो निशान, किसी का दर्द मिल सके तो ले उधार, किसी के वास्ते हो तेरे दिल में प्यार, जीना इसी का नाम है। माना अपनी जेब से गरीब है, फिर भी यार दिल के हम अमीर हैं। माना अपनी जेब से गरीब है, फिर भी यार दिल के हम अमीर हैं। मिटे जो प्यार के लिए वो जिंदगी, मिले बहार के लिए वो जिंदगी। किसी को हो ना हो हमें तो एतबार, जीना इसी का नाम है। किसी की मुस्कुराहटों पे हो निशान, किसी का दर्द मिल सके तो ले उधार, किसी के वास्ते हो तेरे दिल में प्यार, जीना इसी का नाम है। रिश्ता दिल से दिल के एतबार का, जिंदा है अभी से नाम प्यार का। रिश्ता दिल से दिल के एतबार का, जिंदा है अभी से नाम प्यार का। किसी को के मर के भी किसी को याद आएंगे, किसी के आंसुओं में मुस्कुराएंगे, कहेगा फूल हर कली से बार बार, जीना इसी का नाम है। किसी की मुस्कुराहटों पे हो निशान, किसी का दर्द मिल सके तो ले उधार, किसी के वास्ते हो तेरे दिल में प्यार, जीना इसी का नाम है। थैंक यू।
Thanks a lot, Simabreed, for this mesmerizing performance. Will everyone please thank her for cheering the event. So next, as Sora was talking about A Man Who Knew Infinity, have you seen that movie? No, I haven't. Why? Okay, so let me tell you an interesting scene from that movie when Ramanujan was actually sailing towards England with the ship. So one of his co-passengers was telling him that, do you know how far London is from here? It's more than 6,000 miles. And can you imagine how far is this? And Ramanujan replied to him so calmly that, man, I have known numbers much more greater than that. So that really justifies the fact that why he is known as the man who can actually visualize the infinity. So I really suggest you please go and watch that movie, and the audience also, if someone have not seen that movie, you can definitely watch this biography.
After listening this event, I will surely watch this movie as soon as possible. In order to enlighten us more about life of Shinyuasan Ramanujan and history behind National Mathematics Day, it's time to invite Miss Adiba for a short talk. Please give a big round of applause to call her on the stage.
I, Adiba Zaidi, research scholar in Department of Mathematics and Statistics. Today, we are here to celebrate the National Mathematics Day. It is celebrated every year on December 22 across the nation to recognize and celebrate the work of India's gem, Shinyuasan Ramanujan. It was on this day in 1887 the Indian mathematical genius Shinyuasan Ramanujan was born in Erode, Madras. This is a picture of his house, which are now known as Chennai, situated in Chennai. National Mathematics Day was first observed in 2012 when former Prime Minister Dr. Manmohan Singh declared this day as a National Mathematics Day on February 26, 2012, when he was visiting the Madras University in order to pay tribute to Ramanujan's achievement and celebrated his 125th birth anniversary. Since then, it is observed every year on December 22 to honor Ramanujan's work in the field of mathematics. In 2017, the day's significance was enhanced by the opening of the Ramanujan Math Park in Kappam in Chittor, Andhra Pradesh. The legendary mathematician Shinyuasan Ramanujan was a self-taught mathematician. He didn't have any formal training in mathematics. Despite of this, he made extraordinary contribution to the world of mathematics. As Ramanujan was one of the most influential mathematicians of his time. Till today, we haven't idea how he got many of his results. He made extraordinary contribution to mathematical analysis, number theory, infinite series, continuous function, and many more. He loved to play with numbers since the childhood. Well, he has done lots of research in mathematics and amazed the world. Let's try to take a glimpse of his mathematical life and talk about some of his famous discoveries. First is Ramanujan magic square. This looks like a simple square, but this square is made by Shinyuasan Ramanujan. So what is special about this square? The sum of numbers any row is 139. The sum of the columns is any columns is also 139. The sum of the diagonal elements is also 139. The sum of the corner numbers is also 139. Look at this colored box, its sum is also 139. And try this pattern, its sum is also 139. And look at this central square, its sum is also 139. Now try this pattern, its also sum is 139. Try this possibility is also, this sum is also 139. Do anyone know what is the date of birth of Shinyuasan Ramanujan? It's 22 December 1887. That is 22/12/1887. That is the first row of this magic square. Now, the question is this square is unique or Ramanujan has some special mysterious date of birth, or is there any hidden mystery behind the number of 139? But no, you can also make your own magic square by using this formula. Well, Ramanujan loves to play with infinite series. They are one of the famous series known as the Ramanujan Summation, which is actually the number of natural numbers. Sorry, sum of the natural numbers. Let's try to do this. This series is known as a Ramanujan Summation, but he take a series S1 where we have take 1 and even times,
with alternative plus minus sign. Now he add this, so after cancellation, 1 cancelled with minus 1 and we got S1 is equals to 0. Again, he took this same series, now the 1 comes in odd times. So similar way, he do this cancellation and we got S1 is equals to 1. Now, if we add S1 and both S1 values, we got to S1 is equals to 1, and by this we got S1 is equals to 1 by 2. After this, he take another series, that is in which odd number comes with positive sign and even number comes with negative signs. Again, he take this, and after adding this, we got 2s2 is equals to 1 minus 1 plus 1 minus 1 plus 1 minus 1 and so on. Now look at this one. We have already proved this value is 1 by 2. So we can write 2s2 is equals to 1 by 2. So by this we have s2 is equals to 1 by 4. After this, he take the original one series, that is 1 plus 2 plus 3, that is a sum of the natural number, and he write s2 like this, and after subtracting this, he got s3 minus s2 is equals to 1 1 cancel out, 4 3 3 cancel out, 8 and 5 5 cancel out, 12, and similar pattern we can write plus 16 and plus 20 and so on. So we can take 4 common, so we got 1 plus 2 plus 3 plus 4 plus 5 and so on, and this is the actual series S3. So we can write in place of this S3. S3 minus S2 is equals to now 4S3. And we know this S2 is equals to 1 by 4. So we have minus 1 by 4 is equals to 3S3. And by this we have S3 is equals to minus 1 by 12. So you have seen how Ramanujan proved this series. Now we move forward and now talk about the Hardy-Ramanujan number. You knew there is a very interesting incident behind this. On one occasion, J.H. Hardy, a British mathematician, took a taxi to visit him on his sick bed and noted that the cab number was 1729. After greeting Ramanujan, he remarked, "What a dull number 1729 seemed to be." Quick as a flash, Ramanujan corrected him and said, "No, Hardy, it is a very interesting number. It's the smallest number expressible as the sum of two cubes in two different ways." You can see this like this. So this example shows that how Ramanujan knew about the numbers very well. And there's a lots of discoveries by Ramanujan which shows how this factor suits this very well, how he knows and how he predicted that this number is almost closer to an integer. And he also gave a few more spectacular examples like 3 to the power 5 root 58 and claimed that these numbers are actually very close to an integer. After I think 65 years, in 1975, an American popular mathematics and popular science author, that is Martin Gardner, he made a claim that actually this number is an integer as Ramanujan predicted. After using modern technique, it was proven that truly this number is very close to an integer. No one knows till now how Ramanujan come to know this without any use of computer and modern techniques. Also, there are many more results given by him which are mystery till now. Isn't it amazing? He used to say that he got visions and dreams about formulas and theories. He wrote while asleep he had a usual experience. There was a red stain formed by a flowing blood, and when I was observing it, suddenly a hand appeared and began to write on the screen. I became all attention. That hand wrote a number of results in elliptical integrals. They stuck on my mind. As soon as I woke up, I committed and then to write. This dream and this incident shows that how much adapted Ramanujan towards the mathematics. Nobody understood his work, but he did. How over compiling, I think, 3,900 mathematical results and equations to getting discovery named after him, his numerous assertions in mathematics opened up a new vistas of mathematics research. He anticipated and inspired so much quality of 20th century mathematics. His formula has been used to solve ancient mystical mathematical mysteries. They have also inspired many of the most important mathematicians of modern era. Ramanujan's work from his deathbed has inspired vacuum physics, the theory of Mach-Theta function, quantum gravity theory, and many more. Before he died, at the age of just 32 from tuberculosis, Ramanujan left behind 3 notebooks with pages containing 3,500 unpublished results, full of enigmatic theories and formulas that will keep scientists busy for many years to come. It's truly amazing and fascinating to think that he made these discoveries only that short span of his life, and led all of us to wonder what would a mathematics be like today had if he lived a proper long life. Seriously. If I continue to say more about this genius, magician, incredible, miraculous, and unbelievable talented man, then my talk goes on and on and on. So I would like to stop my words with the famous quote of Sri Ramanujan. He said, "An equation means nothing to me unless it expresses a thought of God." Thank you.
Thank you, Adiba, for this amazing and informative talk. Now, students are ready to present their posters. Here, I would like to mention that there would be first and second prize for poster competition. I request all the faculty members and judges to please pay your kind attention to prepare the results. I request all the participants to please be ready with their posters. In the list of participants, first I am calling team 1. And in team 1, I am calling Saurabh Kumar and Shivan Pal. Please come forward and present your poster.
So, again, here I am. Last night, we were discussing something, actually, long before. And Saurabh showed me a video which was on Banach-Tarski paradox. And to explain you, I want all of you to go back in your childhood when you used to ask for chocolate from your father. How amazing it would have been if your father gave you chocolate and you break it into at least 5 pieces, and then just by reassembling it, you can have exact 2 copies of that chocolate. You just created the chocolate out of nothing. It would have been really amazing if we could actually do that. But one might say, don't be silly, Sivankar. What are you talking about? No one can create something out of nothing, apparently. You can create at least the universe, not the chocolate. But in 1924, Banach and Tarski proposed a paradox. And it is called paradox because it is mathematically true. But in reality, whether it is true or not, we are not confirmed about it. What does it say? In simple language, it says that if you have a piece of paper or anything, a board, and if you make at least 5 pieces, not less than 5 pieces, at least five pieces, and you rearrange them, then just by rearranging, you can create one more copy of it. A stronger version of it also considered as P and sun paradox, where you can chop up a P and just by rearranging, you can create a P of the size of the sun. This is a very interesting thing. This seems completely impossible in the real world, but some theoretical physicists did experiment in their colliders, the subatomic particles collider, where they collided some particles and not a single particle was broke. But still, after the collision, there were more particles than there were in the beginning. So it is, we can notice that something is happening. We are not yet sure that whether it can happen in the real world. For this to happen in the real world, things has to be infinitely complex. And that's not true in the real world. But still, this shows the beauty of mathematics, because if you look at the history, then we can clearly see that in mathematics it usually happen. At first, we find something and it seems completely out of the world thing, and even the mathematicians say that this cannot be useful in the real world. Who knows? Someday someone will come up and we will know some kind of use of this theorem also, and you might be a job in after that. Thank you very much.
Thank you so much, Shubham, for this informative presentation. Next, I would like to call Pyle and Neetu for team settings to present their poster.
Good afternoon, all of you. My name is Neetu. My name is Pyle. The topic of our poster is fractals within words. Just as we all know that in Euclidean geometry, we study about the objects having integer dimensions, and but in fractals we come across with the complex geometric shapes having fractional dimensions. Fractals in the political geometry, there is identical shapes, but in fractals there is a dimension, fractional dimension. There is a 5 example of the fractals. First is the Cantor set, second is the quadratic Koch Iceland, and the Koch snowflake, Sierpinski triangle, and the Sierpinski carpet. Firstly, we explain the Koch snowflakes. In the Koch snowflake, we take the equilateral triangle. In equilateral triangle, the middle of the triangle, we draw another equilateral triangle. With this equilateral triangle, first line have 4 parts. The fractals have dimension log n by log n. In Koch snowflake, there is n log n by log n, and log n is the subsets and the log n is the magnification factor. In Koch snowflake, n is the 3, because when we draw equilateral triangle, the one side has the 4 part, and the 3 sides, there is a 4 into 3, that means 12 part. The side like this, 3 into 4 into n, there is 12 n dimension. In the Sierpinski triangle, there is a finite area, and in the finite area, there is a self-similar sets. In equilateral triangle, firstly we draw equilateral triangle. Inside this, we draw equilateral triangle with equilateral triangle. In the quadratic Koch Iceland, we draw a square. In the square, we draw 90-degree left side, 90-degree right side. With a similar pattern, we draw Sierpinski carpet. And in the Cantor set, there is a totally disconnected set. It says measure 0. Fractals has dimension log n by log n. In Cantor sets, there is a 2n subsets and the 3n magnification factor. When we take n is equal to 1, then in the candlestick's dimension has log 2 by log 3. Fractals used in the nature, in the leaves, in oceans, in mountains.
Thank you, Payal and Neetu, for this creative poster presentation. And it's time to call our last participant, Simaprit Kaur. Please come and present your poster.
So, I would like to start with a question. Is it possible for a vessel to have infinite area and finite volume? Yes. Physically, may not be, but in mathematics, yes, it's possible. Let's see how. Imagine you have a vessel, and we want to fill it with paint, and it can be filled. But if you want to paint it, it's not because it has infinite area. The name of this vessel is our vessel is Gabriel's horn. The name is the name refers to tradition, and you might have seen the statue of an angel, Gabriel. Its name after this. And how mathematically is possible for a vessel to have infinite area and finite volume. So what we do here, we take the graph of 1 upon x, y equals to 1 upon x, and we rotate it along x-axis. And in three-dimensional, we get a shape named Gabriel's horn. So if we do integration, and by doing some calculations, we can prove that it has volume equals to pi and area infinite. So this is also called Painter's paradox.
Thank you so much, Simaprit, for this beautiful figure. And now, it would be unfair if we don't appreciate these talented students with a big round of applause. Poster presentation has So, participants have made cheerful designs outside the mathematics lab. Please have a look at them. Don't you guys feel that it's time to have some tea and snacks? Winners for all the right competitions will be announced after a small tea break. So we request you all to please gather back here after 20 minutes for the prize distribution ceremony. Now you guys can have high tea and snacks. We have 10 minutes. At 4 we will begin with the Good evening, sir. Sir, are we audible? Good evening, sir.
Hello. Yeah, you're audible. Yes.
Sir, actually, people are taking refreshment outside, and there was a small break, and schedule was delayed by 10 minutes. So
Oh, okay.
people are coming back. So if you can,
It will take 10 minutes, please.
Okay. So should I join after 10 minutes
yeah,
or?
yes. Sir is also not here. We were calling him, but he's not here.
Okay.
He's
Okay.
there only.
So sorry for the delay.
Yes,
Please wait for the-
No. I was informed to join 3:50.
Yes,
So
sir. Yes, sir. That's what. But the program was earlier program was delayed a bit, so that's
okay.
why everyone is there is taking refreshment.
Okay. No problem. No problem. So
I'll tell sir to call you whenever after 5 to 10 minutes.
okay, no problem. Okay. Or if you want, then I can stay here also if somebody wants to discuss
But
with
you'll
me.
be all alone here, so if you can.
Okay. No problem. No. Okay.
Okay,
Fine.
sir.
Fine.
Okay, thank you, sir.
सब लोग मोबाइल से ज्वाइन कर लो, उसको वॉल्यूम बंद कर लो, स्पीकर को पता चले कि लोग हैं।
ये बात भी सुनो।
कैमरा भी इस तरफ की वो तरफ है ना, कैमरा बाद में
नहीं, उधर वो चल रहा है कैमरा, वो ऑन नहीं है, ऑन क्यों नहीं?
वो दिखा रहा है, स्क्रीन दिखा रहा
सर वो है, चलिए शुरू करिए। वो तो ज्वाइन कर चुके हैं। पूछना है
मैसेज हो गया
कौन कर रहा Yes, yes. ज्वाइन कर लीजिए सब लोग।
A very good evening, everyone. On the behalf of Department of Mathematics and Statistics. A very good evening, everyone. Hello. A very good evening, everyone. On behalf of Department of Mathematics and Statistics, I welcome you all to this event to celebrate National Mathematics Day, a birth anniversary of legendary Indian mathematician Shinyuasan Ramanujan. And I also extend my warm welcome to our today's speaker, Dr. Tapas Chatterjee, who is an assistant professor in Department of Mathematics at Theorem. He is going to deliver his lecture on the topic Life and Mathematical Legacy of Shinyuasan Ramanujan. Now, as per the tradition of the university, we will start with the university anthem. So I request you all to please stand up for the university anthem.
First of all, I request Professor Goldbach, Head of the Department of Mathematics and Statistics here at Central University of Punjab, to formally welcome our guests and participants.
Thank you, Dr. Siddew. So, Honorable Vice Chancellor, Central University of Punjab, Professor R. Tiwari sir, Dean in Charge Academic, Professor Ramanujan Summation, our expert for today's talk, Dr. Tapas Chatterjee, all deans of all the schools, HODs of all the departments, all the faculty members, research scholars, the students, and all other dignitaries present online on this platform for this event. I welcome you all on behalf of Department of Mathematics and Statistics and the whole organizing committee of this event for this auspicious occasion. So today we are going to have a invited talk of Professor Tapas Chatterjee entitled Life and Mathematical Legacy of the great Indian mathematician Shinyuasan Ramanujan. So I formally welcome you all in this event. In the morning session, I have already portrayed some things about the Indian mathematics, and I would like to add something that mathematics is so important in everyone's life that even in our Vedas there are some yuktis which has said like this: Yatha sikha mayuranam naganam madyo yatha tad vedam satsaram gaditam murdhan vartate. वेदांत ज्योतिष में कहा गया है कि जिस प्रकार मयूरों में शिखाएं, मयूरों की शिखाएं और सर्पों की जो मणियां हैं वो शरीर के शीर्ष भाग पे स्थित होती है, विराजमान है, उसी तरह जो गणित है वेदों और शास्त्रों में सर्वोपरि स्थान पे विराजमान है. One thing more I would like to add, which was said by Mahavira, the great Indian mathematician from Jain tradition. And Mahavira has said that Bahuviri Pralabhi Kim Vilokai Sa Charachare Yaktim Jindas Tatsarva Gaditin Vina Nahi. जिसका अर्थ है कि बहुत अधिक प्रलाप करने से क्या लाभ है. महावीराचार्य कहते हैं कि बहुत अधिक प्रलाप करने से क्या लाभ है. इस सचराचर जगत में, यानी कि जिसमें प्राण है, चाहे वो पेड़ हो, पक्षी हो, ह्यूमंस हो, इस सचराचर जगत में जो भी वस्तु है वह सब गणित के बिना समझना संभव नहीं है. तो आप कह सकते हो कि what is the use of much speaking? In English we can say that he sees that what is the use of much speaking? Whatever objects exist in the moving and non-moving world cannot be understood without the base of mathematics. So we can see this is the importance of mathematics. So once again I welcome you all with these few words. I will not take much time. So once again I welcome you all in this event. Thank you.
Thank you, sir. Now I request Dr. Sachin Kumar to please introduce the speaker.
I'm really feeling honored that I've been asked to introduce one of the person that is doing great work in this area. And first of all, thanks Dr. Sitaji for joining with us on this special occasion. Dr. Tabascharan is currently an assistant professor in Department of Mathematics at IIT Roper. He obtained his doctoral degree from Institute of Mathematical Sciences, Chennai. After obtaining his doctoral degree, Dr. Chatterjee joined as a postdoctoral fellow in Department of Mathematics and Statistics in Queen's University, Kingston, Canada. He was also a visiting researcher at the Institute of Computational and Experimental Research Mathematics in Brown University. Later, he was a visiting professor at the University Marie Curie, University of Paris, France, during the May and June 2017. He was visiting professor at Nagoya University, Nagoya, Japan, during June-July 2018, and a visiting professor at Paris Sorbonne University, Paris, France, during June-July 2019. His researches focus on various topics in number theory, and he has a very good work in the illustrated. So once again I thank Dr. Secretary for joining us. Thank you.
So, am I audible? Hello, am I audible?
Yes, sir.
Oh, okay. Yeah, so thank you, Professor Gauri Shankar, for this invitation, and Professor Sachin Kumar for this invitation and kind words. Okay, so should we start our this journey, or? Hello. So should we start?
Yes, sir. Yes, sir.
Okay. So I need to present, right? Present my screen. Okay. So please feel free to stop me if you have any problem, like understanding something, or if you have any doubts, question. Okay. Please feel free to. So is my screen is visible to everyone?
Yes, sir.
Okay. Yeah. So let me just introduce. Obviously, this man needs no introduction, and we are going to actually enjoy his life and journey, maybe the next 1 hour. And I will try to explain everything in simple words, though many of his work cannot be explained in simple words. So I have tried to make it as simple as that for a public talk, so that everybody can enjoy. Okay. And this is a story of a college dropout. So we already know, like, many few famous college dropouts like Bill Gates, Mark Zuckerberg, and then Steve Jobs. These people are very famous. But Ramanujan was 2 times college dropout. Okay. And his life was not less than any of those people, those billionaires which I just told you. It's more exciting. So let me start with these 2 books. Okay. And the first book is the name of the book, title of the book is The Man Who Knew Infinity. It's by Robert Kanigel. So this was first published in 1991, and later there was edition in 99 and other things. So this is the first, probably the definite biography of Srimad Ramanujan. But before that, obviously, there was many written note, many books was there. But probably this Kanigel book was the place where you will have maximum details on his life and his journey. And so I recommend this book. This is a beautiful book for everyone, not only a mathematician, for everyone. And if you are a mathematician, if you want to know more about his mathematics, then the second book, this is called The Mathematical Legacy of Srimad Ramanujan, and this is written by Professor Maruti Ramurthy and Vijay Kumar Murthy. And Professor Ramurthy was my postdoctoral mentor in Queen University. And I'm very happy to obviously share this book also. This is one of the classical literature on work of Ramanujan. So he's focused on more on mathematics, this book. Okay. So the first book is actually more famous. It was actually bestsellers. And there was a famous movie made on this book. And the movie name obviously as same, The Man Who Knew Infinity, starring Dev Patel as Ramanujan and Jeremy Irons as G.H. Hardy, famous Hardy. And this movie is also, I think, one of the best I have seen actually. So I also recommend people to watch. And this movie was actually promoted by two of the great mathematicians of our generation. One is Ken Ono, and the second person is none other than Manjul Bhargava, who was a film medalist. Okay, so these two references are very widely cover the life of Ramanujan, and for general audience who are interested, they can start with this. This is highly recommended. Okay, now let me begin our journey. So the story of Ramanujan is actually a story of mathematical discoveries and innovative originalities. And he actually came from a very small, humble village. And most of his knowledge was actually self-taught. And we will actually give some kind of brief idea of his life and his work, his contribution to the mathematics. Okay, so let us start with his early age. Shinyuasan Iyengar Ramanujan was born on December 22, 1887 in Erode, a small village in Tamil Nadu, at his maternal grandfather's home. And he was there his childhood with his maternal grandfather's place. But unfortunately, his grandfather lost his job, and then he was forced to return with his mother to his father's place, which was at Kumbakonam. Around at the age of 6-7, he returned to his father's place, which is Kumbakonam. And his father was also a clerk at a local sari shop with a very, very small salary. So it was very difficult to afford the family those times. And this is the Ramanujan house at Kumbakonam. And the name of the street is called Sarangapani Sanidri Street in Kumbakonam. Listen, you can easily find out this picture in internet, and this house is still there in Kumbakonam. Okay. So this is kind of his early age, where he started his primary school there. So now let me tell you one more story here. So how he attracted into mathematics. So those days, generally students used to come from small villages to learn mathematics, learn any subject to a properly little bit bigger town compared to the villages. And Kumbakonam was a little bit bigger town, where there was a government college called Kumbakonam College. And two of the students actually staying in Ramanujan's house for kind of, nowadays it's called PG, we call it PG. But those times, people used to stay someone else's house and complete their studying. So there are two students who are staying, who are doing their FA degree. So FA degree is kind of, right now we call it +1, +2, like 11, 12. Those times it's called FA degree, or intermediate, whatever. Yeah. And Ramanujan actually borrowed this book of S.L. Loni by Plane Trigonometry from those students. And then that time Ramanujan was kind of 10 or 11 years of old, around that page. And he borrowed this book of S.L. Loni's trigonometry from those students who were staying at their place. And he started mastering on those subjects, trigonometry, and in fact that book also have some idea of calculus. So this book was kind of the first encounter where Ramanujan started liking his mathematics, and his child prodigy was actually seen from his idea of completing and learning the subject at the early age, like around 10, 11 years old. Okay, but after that time, he went to college. I see that same college, Government College of Kummukanam. I will give you more details later, little bit later. But around that time, Ramanujan actually got attracted by a very, very innocent kind of a collection of results, and this is by due to G.S. Carr. It's called Carr Synopsis. So he borrowed this book from the local library around the age of 15, 16, when he actually joined that college also, Kummukanam College, for his FA degree. So FA means first degree in arts kind of things. Okay, so those time mathematics used to get arts degree like FA in arts, then BA in mathematics, MA in mathematics. So those were the structure. So which is equivalent to FA means equivalent to our 11, 12 standard. Okay, you can say junior college also. So this is the book, G.S. Carr, this synopsis in mathematics, and this book actually contains many statement results without proof. Some are conjectures also. And Ramanujan actually, this book is actually changed his life. So he borrowed this book from local library and he started proving all the results, which is mentioned there without proofs. He started giving proofs of as much as possible. Okay, but due to, as I told you, the financial condition of his father was not so much strong, and he could not afford like this paper, everything. So he used to do all those things either on the floor, house floor, or on the slate. So so this is my also child memory. I also used to do in slate, I remember. So, and then after doing this calculation, he used to rough those things by his elbow. So if you see Ramanujan, some of the picture, his elbow was very kind of pale. So that because he used to rough his this to erase those things by his elbow. Okay. So this was this amazing journey start, and after whenever he was satisfied that he got some results or new thing, improved thing, he used to note it down on one of his notebooks. That I will show you all those pictures and everything, and then I will show you how it connected with me. Okay, so so now so around that time in 1913, at the age of 15, he admitted to this government college Kummukanam. But unfortunately, he fails FA degree. That because that FA degree involves subject like sociology, Sanskrit, and Ramanujan failed both in sociology, Sanskrit, and I think physiology or another subject. He was only focused on mathematics, nothing else than other subjects. So he fails all the subjects other than mathematics, and obviously he was. I mean, with this incident, he was not happy, and his father was also disappointed. So there was lots of misunderstanding going on in his family around that time. So what Ramanujan decided, so he decided to leave home, and he left home actually around that time, to the 1903. So he left home, and nobody knew that initially where he was. So his mother was very much actually. His mother was very much anxiety. Where is Ramanujan? Nobody knows. So he asked his father to at least give some advertisement. And those time there was a very famous newspaper which is still late. It's there. It's in the Hindu. I hope some of you must have read this newspaper, the Hindu. Those time, early 1990s. This newspaper was only tri-weekly, so it comes only 3 times in a week. Now it is daily newspaper. So Ramanujan father actually gave this. Okay, so before that, let me show you the picture of this Kummukanam College. This is the modern day picture of obviously Kummukanam College, government college. And the Ramanujan father, what did he give this this missing things, missing advertisement, and a missing boy. You can read it that to the editor of the Hindu. Sir, kindly insert the following in your widely circulated journal. A Brahmin boy of the Vaishnava Telangana caste named Ramanujan, of fair complexion and age about 18 years, was still recently a student of Kummukanam College. He left his home on some misunderstanding. And his guardians are very solicitous about the boy returning home. He stayed at Rajamundry. So Rajamundry, yeah. So Rajamundry is now a part of modern day Andhra Pradesh, but in those British India, it was all part of something called Madras Presidency. So this Madras Presidency was as big as till Visakhapatnam, probably, yes, around that time. And people used to know both the language, Tamil and Telugu. And Ramanujan also was fluent in both the language, Tamil and Telugu. So he can easily move any place in this Madras constituency around that time. So he was in Rajamundry for a month. He stayed there, and then also he disappeared. Nobody knew where he was. So finally, his father name is Shinyuasan, obviously. You know that Shinyuasan Ramanujan, Shinyuasan is the name of his father. Ramanujan is his name. Okay. So his father, Shinyuasan Raghava Iyengar, gave this name. Okay. And I don't know what happened, but after some time, he actually returned back to Madras. Probably due to maybe this advertisement or something, I don't know. Then he came back to join this college called Pachayapa's College in Madras for the second time for his BA, this FA degree. The first time, because of that, he left his college, Kummukonam. He's kind of, you can say, college drops out. And second time also he joined there, but unfortunately the story repeat. And again he failed there to all these non-mathematical subjects. Unfortunately, same thing happened here also. Okay, so am I audible, or so is there any, everything's fine, right? Can anyone?
Yes, sir.
Okay, yeah. Okay. So same story actually repeat, and Ramanujan also again failed his FA degree. He could not clear that FA degree also in Madras. So those time it is not Chennai, it is called Madras. Okay. So so again he was like very much. I mean, he did not know what to do after this. He was very much anxious. His family was also worried about it. And he was trying to meet 2-3 people there in Madras. I will tell their name also after some times. Okay. So so around after a few years, so his mother realized that it is better to like every parent has worried about their children. So his mother, what his mother did, his mother actually managed to agree him for his marriage. And this 1909, 14 July, his mother actually found a girl named Janaki Ammal, and the girl was 10 years of old that time. And Ramanujan got married to this lady when the lady was at the age of 10. And it was very common those times, actually. This kind of child marriage was very common to those days. And but obviously rule was there, you have to stay at your father's home till you become kind of you reach to your puberty. And then around at the age of 13, this Janaki was Ramanujan's wife, and his mother came to Madras to stay with Ramanujan, because his mother was so much worried about Ramanujan, whether he can left and go some places. Nobody knows what he's thinking, right? So his mother decided to stay. So he came with his wife to Madras, and they stayed to first they stayed to one small place. Then later they came to a place which is called Tiruvellikeni. You can see the railway station also in Madras. Also in short form they call Tribliken. You can see that house also still there, Tribliken Ramanujan's place. Okay. So this was a story, and then around that time, after this marriage, he thought that now I should at least try to get some job, other things, and this was also difficult to get a job without any degree, right? Any degree, FA degree, or at least like those time you need BA degree for good jobs, but at least you need FA degree for some little bit small level job also. But finally, he actually managed to get job he got letter from a friend to meet a professor in Presidency College, Madras. There was a college named Presidency College in Madras also that time. So these colleges are actually comes under Madras University those time. And let me just recall one thing here. So the first college in India was established in Calcutta in 1817. Later, that was extended to University of Calcutta, which is called Calcutta University. Nowadays, Calcutta changed it to Kolkata. And then, similarly, around that time, the Madras University also established around 1850s. And then there was a man named Sir Ashutosh Mukherjee, who was kind of, we called him the kind of father of modern Indian mathematics. Okay, so he was a mathematician, come a barrister, lawyer, come many things. He was a polymath. He knew many things. Then later, when he was vice chancellor of Calcutta University, he brought English mathematician, everything to promote modern mathematics in India. Because before that, Indians are used to learn on Vedic mathematics and other things, not the European mathematics. So those train was also there in Madras University. There was many British professors was there in Madras University, like Calcutta University. Okay, and Ramanujan met some of those people and some of the Indian mathematicians also. And I will tell you that story also after some times. Now let me tell you, before around that time he got there's actually professor at Kumbakonam College. His name is P.B. Sesu Iyer. So Sesu Iyer knew Ramanujan that he had some idea of mathematics. So he wrote a letter to another person who was the distinguished, I think, some administrative officer, but the person is also a mathematician from Presidency College. His name was Ramaswar Rao. And then finally, helped Ramaswar Rao, he got a job in this post trust office of Madras. Okay, so what happened to this? Hello, am I audible?
Yes.
Yeah. Yeah. So he did not have any degree, so he got this protest of this clerical job. Like he need to keep track of those accounts, what are the money involved, everything. Okay. But around this time, he was very lucky that his immediate boss, what we call boss, immediate boss was a person named Narayan Iyer actually, and he was very helpful. Because Narayan has also background from mathematics, he realized that Ramanujan has an extraordinary talent. So he allowed Ramanujan to do mathematics at free times. So he used to do mathematics during night and used to do job during daytimes when he was in Port Trust of office at Madras. Okay, and around that time, Ramanujan actually wrote down most of his work in these notebooks, these 3 notebooks. You can see these notebooks. These are Ramanujan original handwriting. Okay, so 1 minute. So let me fill it. And later, obviously, 2000. Okay, so now let me tell you the connection between these notebooks and me. What I had these connections. So I was a PhD student at Institute of Mathematical Sciences from 2008 to 2013, and around that time, 2009, Tata Institute of Fundamental Research, they decided to preserve this original copy of Ramanujan. To digitize those things so that quality will be improved and it will be safe. Because the original, all those copies are in Madras University, Mathematics Department Library is called Ramanujan Institute of Mathematics, Madras University. And 1 copy is there in Institute of Mathematical Sciences where I did my PhD in that library also. So what did Tata Institute of Fundamental Research decided to do this thing because 2012 was Ramanujan's 125th birth anniversary, so they decided to do these things. And what they did, so they tie up with the famous library which is called Roja Muthaya Library at Chennai. from our institute. So our institute had fourth cross-street, Taramani, it was in third cross-street. So the local mathematician, famous mathematician, was the director of Institute of Mathematical Sciences, Professor R. Balasubramanian, and who actually allow us to go to Rojamutara library and do the proofreading. So like me, there was few more mathematicians were involved in this process of proofreading of Ramanujan original book to this making digital treatment of the book. And I am very lucky to feel myself that I have touched all the 3 hand notebooks of Ramanujan by my hands and corrected many of the typos, what was there during this process of digitalization by Rojamutara Library in Chennai. Okay, like many other mathematicians from Institute of Mathematical Sciences and Chennai Mathematical Institute, they are also involved in this process. Okay, so this process was a long process, probably 1 year, 2 year process. And the 22nd December is the National Mathematics Day. From that time onwards, 2012, we are celebrating this National Mathematics Day. So this is the story of Ramanujan old notebook versus the new digital version. And there was few copy, which is called that collected copy, which is very costly, around 13,000. And there are, I think there are only few copies they printed for that to Tata Institute. But other you can actually find out the paperback. This is also not very costly, around 1,000 rupees probably. You can. So these are also kind of your, it should be in your collections. Okay. So this is a beautiful story of Ramanujan notebook. Now get back to again his life. Yeah. So so now let me talk about something about Ramanujan's research. And Ramanujan first paper. So it was 1911 when Ramanujan was at the age of 24. He published his first paper on Bernoulli numbers. Okay, and it was published in Indian Journal of Mathematics. And so these numbers are actually naturally arises when you derive the formula of sum of first kth power of in natural numbers. And let me just give brief idea how Ramanujan got the idea. So it was obviously well known that sum of in natural number is n into n plus 1 by 2. It was well known probably at the time of Euclid probably. And there was many story involving this. Many mathematician has encountered many story. But let me tell you how Ramanujan got interested to these things. So this idea of the summing of higher power of natural number was again by a famous Indian mathematician. His name is Aryabhatta the second. It should be the second. So his father was also Aryabhatta, but his father was not the famous. He is the famous person. So Aryabhatta obviously the person who invented zero, that we remember him, but he also invented many things. He also invented infinity, for example. And idea of infinity also due to Aryabhatta. And also Aryabhatta also derived that how to get formula for sum of square of first natural number or sum of cube of first natural number. So these ideas also due to Aryabhatta. Okay. So this was the point which triggers Ramanujan to generalize this kind of identity, and he started doing the generalization. So as I mentioned, Aryabhatta knew that n plus 1 whole square minus n square is of this form, and then if you just sum those numbers till 1 to n, then you see that in the left hand side telescopes come, so everything get cancelled. Only the higher term n plus 1 whole square minus 1 will be left. And right hand side is very interesting. Right hand side is actually coming from this kind of sums, skn's, which is sum of kth power of natural numbers. Okay. And then using this idea, Ramanujan actually derived the results on Bernoulli numbers. Okay. So so what is Bernoulli polynomials? So Bernoulli polynomials are actually polynomials coming from this number Snk, which is polynomial of degree k plus 1, and you can actually prove that the rational coefficients, this polynomial, the coefficients of the polynomials are rational numbers whose leading terms is of this form n plus 1 by k plus 1. and then you can do manipulation sum and get these results. Okay. Obviously, later many people work on these polynomials. Ramanujan was not the first person. Euler also had some work, obviously, on that, but Ramanujan has more general work on this. Okay, so this was the first paper of Ramanujan published in 1911. And now let me tell you the famous story of collaboration with Hardy. Okay, and this is probably everyone knows, but let me just briefly tell you. We know that in 1914 Ramanujan went to England to work with G.H. Hardy. And I still remember I was in school when I get a book on some Indian mathematicians where I read about Ramanujan also, along with Gagan Sarkar, who was a student of Sir Asutosh Mukherjee, who was kind of founder of that. And then I came to know about Hardy from that book. And the first person that came to my mind, that who is Hardy, I thought this is the person. Okay, because I knew about this comedian named Laurel and Hardy and Charlie Chaplin during my school days. I thought this is the person, but later I realized no, this is not the Hardy they are talking about. This is the Hardy they are talking about. J.H. Hardy. Okay, so you can think one is a mathematician, another is a comedian. But people had a wrong impression. People feel that nobody helped Ramanujan in Madras, and nobody knew his mathematics, nobody understood. That's why he went to England. And this is completely wrong impression, because there was many mathematicians who helped Ramanujan. And let me tell you a few of this. Okay, so yeah, so people thought that nobody helped Ramanujan, but this is wrong actually. Actually, there are many people who actually helped Ramanujan. Ramanujan also spent lots of his time with doing and working and discussing mathematics with those people, and they stayed. Ramanujan stayed their home also. And in fact, one person I will tell you just with a minute, who actually Ramanujan was staying also his house also around that 1910. Okay, so let me tell you these names: Indian mathematician and Madras. So the leftmost person is anyone knows this person? The leftmost person, because this 3-person name is already written, so you can understand. But anyone knows this person, leftmost person? Can anyone tell me? Okay, so let me tell you. So he is Rameswar Iyengar, who is the father of Indian Mathematical Society. Whatever Indian Mathematical Society today is there, he is the person who founded it. He was a student of Presidency College Madras, and later he founded the headquarters as Pune. And he was the first secretary, obviously. He was not the first president. Later he became president also, president of Indian Mathematical Society. And currently, I think Professor Dipendra Prasad is the president. So this Ramachandra Rao and this Narayana Rao, they both actually helped. Okay. And this Professor P.V. Sesu Iyer, the last person, who was actually a teacher of Ramanujan in Kumbakonam College. Later, obviously, he became a professor at Presidency College, Chennai. Madras, I should not say Chennai. And he actually later suggested Ramanujan to write down the letter to Hardy, because, okay, that story also I will tell you why he suggested. But the person who is actually first understood that Ramanujan has extraordinary talent is this person, V. Ramaswamy Iyer, who is the father of Indian Mathematical Society. Okay, so he is a person who recognized Ramanujan from his notebook. He realized that he must be a genius. So he wrote a letter to meet Ramachandra Rao, who was also district collector there, and he was also a mathematician those times. So Ramanujan went to meet Ramachandra Rao, but Ramachandra Rao did not believe that the work he wrote down in his notebook is due to Ramanujan itself. So he denied. He first denied Ramanujan. But later Ramanujan get help from one of the friend from Presidency College, Chennai, Madras, and meet again Ramachandra Rao. Then Ramachandra Rao realized that it must be true. Okay, because of many things he discussed, all those ideas of infinite series and many things. So finally, these are the a small list. Obviously, there are many British professor at the Presidency College also help him, Ramanujan. But these are the foremost Indian mathematician, or you can say people who knew mathematics those time, who has a great impact on Ramanujan's life. Okay, so so what happened? So around that time, Ramanujan, obviously Ramachandra Rao and Narayana Iyengar, they asked him to send his results to British mathematician, and Ramanujan actually wrote to many British mathematicians. Okay, so precisely he wrote 3% before he wrote to G.H. Hardy. Who are this person? So yeah, so we know that Ramanujan wrote these 4 different mathematicians whose work, and these are the person. So he wrote first the letter to the M.G.M. Hill, then Hobson, then H.F. Baker, and finally G.H. Hardy. Now what happened? So these are the picture, please. So let me show you the picture. This is Hill, this is Hobson, this is Baker, and the last but not the least, the famous G.H. Hardy. Okay, so obviously Hill was not happy with Ramanujan's English knowledge of English. He realized that this person don't know how to write proper English, and his knowledge in mathematics also not clear. So he wrote back to. So this is the response to Hill's, which wrote back to Ramanujan, that on November 12th. 1912, Ramanujan wrote to Hill and sent him some of his work on divergence series and Bernoulli numbers. But he wrote back saying that although Ramanujan had his taste of mathematics and some ability, but his lack of the educational background and foundation need to be accepted by the mathematician. So he did not respond positively. He did not encourage Ramanujan. And same thing happened actually. If you read the Cannigal book, you will understand that Hobson also did not reply, because Hobson was actually going through divorce that time. So he rather did not concentrate on this divorce problem than answering to a unknown person. Okay, and then I think same thing happened with similar kind of thing happened with H.F. Baker also. And all those 3 mathematicians was eminent and also very older at that time. But fortunately, Hardy was very young that time. Young mathematician with lots of energy. Hardy was only, I think, 10 years older than Ramanujan. So when he got the letter, then what happened? I am going to tell you. This is very, very interesting story. So, Ramanujan wrote this historical letter, the first letter. That is because Sesu Iyer suggested him that please write to Hardy, because Hardy is a prominent young mathematician who works in mathematical analysis. So Hardy is more an analyst than a number theorist. Okay, Hardy actually used to work on the more on analysis portion. So because of this suggestion of Ramanujan from his own teacher, Kumakaram teacher, he wrote to Hardy on 16 January 1913. And after a brief introductory paragraph, the letter consists of theorems and formulas for next 10 pages. Can you believe? Hammer is writing a letter with all theorems for 10 pages. And all are like single theorems and formulas. When Hardy received the letter, he could not decide it, actually, whether it was written by a genius or a crank. So he was in dilemma. Is this a real person or some crank who is like fooling around? Okay. So he obviously, because Hardy was also very young, he thought, let us try to spend some investigation or some time on this letter. So what Hardy did, Hardy reaction. Okay, so I will come who is the other person in this picture. So after losing his sleep that night, Hardy called one of his very best, or like one of his very good friend and colleague, Littlewood, J.W. Littlewood, who was also kind of on the same stature of Hardy, little bit older probably, little bit older than Hardy. And he invited Little Wood that why don't you come to my house and look at this letter I got from an Indian clerk who is getting only 20 pounds in a year. 20 pounds in a year means roughly 1.5 pounds in a month. And those time 1.5 pound mean 1.5 rupees kind of thing, Indian rupees for a month. So you can understand his earning those times. So what happened? So that night after dinner, Little Wood came to Hardy's house and they started reading the paper with obviously and they are completely clean bold actually, because most of the result Hardy could not prove by himself. Some of the results was obviously known to Hardy. Something was he did not try something. So there are so many things were happening. So Hardy did not know what to do. So after reading almost 3 to 4 hours, Hardy and Ramanujan, Hardy and Little Wood, they decided that this must be written by a genius. And later Hardy wrote to his biography also. I will tell you later. Okay, so this must be a genius. And Hardy wrote again that a single look at them is enough to show that they could not be written only down by a mathematician of highest order. They must be true. Because if they were not true, no one would have had imagination to invent them. So if those formulas are not true, then it is impossible to imagine those things unless you are proving those things. So somebody must have proved these things. So that was Hardy's idea. And then Hardy wrote back to Ramanujan, obviously. And Ramanujan wrote his second letter in February 1913. So there was at around half a dozen letters they have sent each other, exchanging. Rather, Ramanujan was sending his letter, most of his recent work those time. But Hardy was not happy actually. Hardy realized that this is not the way. We cannot do research by exchanging red letters. Like nowadays also, right? So we are doing this online teaching. So as we realize that this is not the way of learning mathematics. In fact, not learning anything. Okay. So for mathematics, you need like one-to-one like things to discuss mathematics. So Hardy also realized that thing. So he invited Ramanujan many times. But unfortunately, Ramanujan was from a Tamil Brahmin family, and those time it was like superstition to actually cross a river, cross a sea or ocean. This was very much superstition. They call it Kalapani. Okay. So initially, his family was obviously they did not agree. Ramanujan's mother and other people was very much strongly opposed that Ramanujan should go to England. But Ramanujan was also eager to work with Hardy, and suddenly something happened actually. So then one day, this Ramanujan's mother, this is the story. Obviously, we don't know if it's true or false. So what Ramanujan's mother said that he saw a dream from the goddess Namagiri Thayar, who is a very famous god in south part of India, which is actually nothing but goddess Lakshmi. Like in south part of India, they have a different name. Like we say Kartikeya, they say Murugan, right? This is the name. Similarly, we say Vishnu, they say Balaji. Similarly, this Namagiri Ayar is actually goddess Lakshmi, who is kind of their kul devata, kul devi kind of thing. So she saw a dream that the Namagiri Thayar came to the dream of Ramanujan and asked her not to stand in between Ramanujan and his road to success. So he realized that he must allow Ramanujan to go to abroad and cross the sea and to fulfill his dream. So you understand that. So those days his parents are also was understanding. Okay. So then what happened around that time, end of 1913, almost one nice thing happened. There was another famous mathematician named Neville, who was actually coming to Madras University for a course on differential geometry. There was a professor, I think Middleton, someone, I don't remember the name, who invited Neville to come to Madras University for this lecture on differential geometry. It's kind of a semester long lecture. a semester long course. And Neville was also a professor at this Trinity College, Cambridge University. And bingo! And then Hardy realized that this is the actual opportunity. So he asked Neville to meet Ramanujan and invite him, and also so that he can talk to Ramanujan and tell that what is the actual importance to go to England. Okay, so this was the thing happening those times. And then Neville came to India. This is the Neville. The left person is the Neville. Right person is obviously G.H. Hardy, young Hardy. So Neville was visiting University of Madras those times. So he was delivering the lecture on differential geometry. So he actually arranged this fellowship, Ramanujan fellowship, and he managed to Ramanujan make him understand that he should come to Trinity College, Cambridge. Okay. So after that incident, on March 17, 1914, Ramanujan sailed to England to meet Hardy. But obviously, it was a 1 month long journey in ship. Okay, and this is the ship by which Ramanujan actually sailed to England, and he arrived on 14th April 1914, almost after 1 month. So he falls, some seasickness was there. So initially few days he was staying with Neville House. Then after a few 4-5 days probably, Neville took him to the Trinity College to meet G.H. Hardy. Okay, so this is the incident. Now let me tell you one more incident here. When Ramanujan and Littlewood understood that this must be written by a genius, the next day at Trinity College, this Cambridge University, there was a huge celebration. Everybody, Hardy, Littlewood was so happy, they are giving this news to everyone. Okay, and it was written by another great British polymath, Barton Russell. So Russell wrote that the next day, Hardy and Littlewood was so excited, he thought that he found out the second Newton. You know that Isaac Newton, he believed is one of the most influential person in world of human, not only mathematics, everywhere, Newton's influence. So Barton Russell realized that the way Hardy and Littlewood celebrating, and they are believing that they find out some clerk in Madras Port Trust with 20 pound salary in a year is probably the second Newton of the generation. So this is the background story I should share. Okay, so now let me tell you what was the letter. What was the letter Ramanujan wrote? The first letter. So this is the first letter. This is obviously not the Ramanujan handwriting. This is, yeah. So and unfortunately, I don't have Ramanujan handwriting thing which I saw in Madras University. I don't have right now. So I got this person. So this is the letter Ramanujan wrote to Hardy on 16 January 1913. And he wrote that I beg to introduce myself to you as a clerk of account department of the Port Trust office in Madras on a salary of only 20 pounds per annum. I am now at about 23 years age. I have had no university education, but I have undergone some ordinary school course. After leaving school, I have been employing the spare time at my disposal and work at mathematics. I have not trodden through the conventional regular course, which is followed in the university course, but I am starting out a new path to myself. I have made spiritual investigation, this, and last line, see that. So in general, and the result I get in terms of the local mathematician are startling. So local mathematician, like as I told you, this is Ramaswamy Iyer, PV Sesu Iyer, Ramachandra Rao, and Narayana. Those kind of mathematicians. Okay. So then he wrote the introduction, and then he started writing his results. This is that pages from his first letter. You can see that there are all the formulas are mentioned in the page. There are so many formulas mentioned. Now let me just draw your attention in this formula number 7 on right hand side. Can you see this cotangent? Cotangent find values. So these formulas, okay, I will tell you later that how they are related. One more formula. Yeah. So this is another formula. Beautiful. These are all beautiful formulas in first letters. Okay. and some of those are later they call Roger Ramanujan identities. Okay. Okay, I think where is that other formula? Okay, I think there was one page is missing. Yeah, so look at this formula. This page, formula number 7 here. The coefficient of x power n in this infinite reciprocal infinite series is actually the greatest integer of this cosine hyperbolic function and sine hyperbolic function. Okay, I will tell you how they are related actually. Okay, they are related to something called partition functions that I will tell you later. Okay, so Ramanujan had this idea, all those things, he had this idea. Okay. And then his second letter in February, and second letter also was very beautiful. And in second letter, he has mentioned many other formulas, especially the formula number 3. Look at this. This was the result due to Gauss. Gauss knew this thing, but Ramanujan completely gave a new proof, new idea, new insight to look at this kind of integrals. Okay, but probably the most important formula is this most startling formula, which Hardy was also stuck, that you can write down pi, reciprocal of pi 1 by pi is in terms of this kind of infinite series. And another most important formula is this. You see that this E, this Euler number E, which like 2.727717289 something dot. So this is obviously, we know that this is a transcendental number. This is the work of Hadamard, French mathematician. And then pi, which is the ratio of circumference and diameter of a circle, which is also a transcendental number. This is also work of Lindemann, another great European mathematician. But if you take this power, e power pi, it is almost an integer. You see, this is integer 396/4 minus something which is almost an integer, 104.017, some 00 part is there. So though both the part e and pi is transcendental and square root of 58 is a algebraic irrational numbers, if you take this thing, it will be some kind of very close to an integer. Okay, so these are the startling results which involved in the second letter of Ramanujan, and Hardy realized that there is no way only to call Ramanujan to Cambridge University and work with him. Other than that, he could totally actually fooled. He had no idea how to prove this kind of things. Okay. And obviously, this is the famous quote, only a mathematician of highest rank could have written them. They had to be true, for if they were not, no one could have imagination to invent them. This is Hardy's beautiful words. Okay. Okay, so now let me tell you some more pages from Ramanujan's notebook. And there, now I would pardon you to describe some of the mathematics here. So far we have discussed more stories. Now some mathematics, I will try to give very easy way to understand, or very basic way to understand. So this kind of infinite product, you see the left hand side, this product of 1 minus in power n this. So this idea, this product of infinite series exists, this idea of Euler, Leonhard Euler. He had lots of work on this infinite product. But unfortunately, Euler could not, even later Gauss also could not actually prove many interesting things on higher power. But obviously, here is the genius who realized that this kind of product has a very nice generating functions. Okay, and then he himself actually wrote down the first 30 terms of this series on the slate. Can you imagine? The first 30 term of the series on his slate. So, and obviously this function now it is called tau function, this tau n, which is a coefficient of this infinite series, infinite product in terms of infinite sums. Okay, and obviously within this computation, Ramanujan made this following conjecture, and these conjectures are actually changed the course of mathematics in 20th century. Okay, so what are the conjecture of Ramanujan? So first conjecture, Ramanujan said that this tau, the tau function is multiplicative. What does that mean? So that means if you take two integers which are co-prime means they don't have any common divisor other than 1. So 1 is the greatest common divisor among those, like 2 and 5, say 4 and 7, this kind of thing. Okay. So if you took two numbers which are co-prime, and then if you evaluate the values of tau at the product, it is nothing but the first evaluate them and then take the product. So it is nothing but the product of tau m and tau n. Okay, this is the first conjecture on tau function. Say around 1916, Ramanujan wrote that thing. Okay. And second conjecture, Ramanujan said that this is for co-prime. What happens if it is not co-prime? Suppose you have a product of, say, let's say prime power. Then how do you do it? For prime power, he said that this is actually following some second order relation, and this is the relation actually. Tau p r plus 1 is tau p into tau p power r minus p power 11 tau p power r minus 1 for prime, p prime and r positive. Okay, this was the second conjecture, and this is the most famous. It's called the Ramanujan bound. Okay, that this coefficient of that power series, that value of tau p at prime, they are not very large. They're actually bounded by 2 times prime or 11 by 2. So you cannot think that these coefficients are like, okay, let me show you. You may feel that the coefficient in like 1 minus 24, then the mod value is 24, 250, 1472, like this, but it is not it is not going very fast. It's bounded by this. Okay. And obviously next year, like 1917, the first two was proved by Model, the famous mathematician Model proved first two of the conjecture, but his proof was very much mechanical kind of proof, was not giving any alignment of the theory. It was Hecke, German mathematician Hecke, who gave actual proper enlightening proof of Ramanujan first two conjecture in 1936. Okay, so first two proof was okay, but the third problem was much more difficult. What it seems to be, okay, and many like world-great mathematicians, those 10 errors, Selbach, and many other people were involving to think this was the problem, but finally it was solved by a person named Pierre Delling. He was solved this Ramanujan third conjecture as a special case of well conjecture, and he got Fields Medal because he solved this conjecture. So you understand how deep it is. In 1974, Delling solved this conjecture, and he got Fields Medal in 1974. Pierre Delling. And by the way, Delling is actually a student of Alexander Grothendieck. He's also a Fields Medalist. Delling himself is a Fields Medalist. Delling student is also a Fields Medalist. Okay, so these are all series of teachers, students, all are Fields Medalists. And Fields Medals are the highest award in mathematics, is compared as Nobel Prize of Mathematics. Okay, so so you understand the impact of Ramanujan work, which actually made the work of eigenforms, the theory of Hecke things, everything arise because of this Ramanujan's conjecture, the formula. Okay, so now let me go to another very important contribution on infinite series special values. So obviously he knew that you are aware of this Euler's work from G.H. Carr thesis, and like he knew that for this sum, like 1 plus 1 by 4, 1 by 9, so this series converges, and the value is pi square by 6. This result is due to Euler in 1731 results. More generally, you can actually do it for higher power. Instead of 1 by 4 means 1 by 2 square, 1 by 3 square. You can take 1 by 2, 1 plus 1 by 2 power k, 1 by 3 power k, like that. And when k is even integer, then Euler gave a proof using Bernoulli's numbers. But for odd number, it is still unknown actually. we don't know whether these numbers, how they look like actually, these things. Okay, it is still unknown, except for k equal to 3, we know that this is irrational, which is also due to a French mathematician Appert in his very recent paper, I think 1971 paper. Okay, not very old. So this was obviously Ramanujan knew this series, and then obviously let me just give Euler how Euler got these things. So Euler started with this kind of polynomial, and then he find out the coefficients. The coefficient of x will be of these forms. Okay, and then so it is well known that to know the roots of a kind of polynomial, if you have a factor x minus alpha, then alpha will be roots, right? So with this method, Euler have a very rough proof. So Euler noticed that the sine phi function has kind of zeros on the integer point, positive or negative integer, whatever. So you can take like 5 sine pi is 0, sine 2 pi is 0, sine minus pi is 0. This is all 0. Okay. So this idea Euler used, and Euler get the proof. But unfortunately, the proof was not rigorous. So Euler proof was not rigorous, or first proof was. Then Euler gave another proof using another method, obviously. Okay, so this is that idea of Euler's proof. Okay, so just let me quickly go through because I have less time. So yeah, so but it is a person named Hadamard who actually justify Euler work. So Hadamard, what he did, he actually proved those infinite product and gave the complete analysis proper proof. So that proof actually makes Euler results is properly correct. But before that, Euler result was not treated as a correct results. Like results are correct, proof are not correct, kind of thing. Okay. Okay, so now let me obviously this is for k or integer. It is not known that what kind of number is this. Now let me come to the another interesting contribution of Ramanujan. So this is known to Euler also, the 1 by pi in power 4 summation is pi square by 90. In particular, for 2k it is pi power 2k into some rational number which involve Bernoulli's numbers. Okay. So now let's come back to the okay. So so here Euler's theorem. Okay. Yeah. So this is I wrote because I just want to show you one more important thing. So Euler actually find out these zeta values. Zeta 2k's are nothing but sum of 1 by n power 2k. K is for 1 to k is for any integer, and sum n is from 1 to infinity. Okay. And obviously, so this is go a little bit fast. Yeah. So why I showed this thing to show this work of Ramanujan. And look at this Ramanujan's page for Ramanujan notebook. Euler's work was involved to these even natural numbers, but Ramanujan actually calculated this identity for odd values of zeta functions. And can you see it? Zeta 2n minus 1. This okay. Let me show you in better version. Yeah, look at this. Zeta 2n plus 1 plus this series. They have a recurrent relation with by this kind of formula. So the Ramanujan formula also Ramanujan showed that these zeta values link with Bernoulli's number B2k with this kind of infinite sum and finite sums. Okay. So the Euler results was much more actually analyzed by Ramanujan on his notebook. So that's why I showed actually this. Now let me tell you briefly a partition function. I think I have time, some more time. Maybe 5 to 10 minutes. Hello?
Yes, sir. Yes.
Yeah, so let me just briefly finish it because these are very, very important contributions of Ramanujan. So what is partition function? What is the partition? Partition means the number of ways you can write down a natural number. Okay. For example, partition of 1 is 1, only one way. Partition of 2 is 2. You can write down either 1 plus 1 or 2. Partition of 3 is 3. 1 plus 1 plus 1 or 1 plus 2 or 3. Partition of 4 is 5, like 1 plus 1 plus 1, 1, or 1 plus 1 plus 2, or 2 plus 2, or 1 plus 3, or 4. So partition of 4 is 5, similarly partition of 5 is 7, and so on. You can do it, it's simple. And you can write down these numbers in factors of these. And So you see that this partition has a generating function, and Ramanujan knew this thing, that this generating function which is inverse of, so the inverse of this function is called phi function actually, or Euler phi functions, okay. So so the partition function has a power series of this kind of form, okay. So now the question is that, do we have a formula, like given an integer say 1000, do you know how many partitions are there exactly? And as I remember, I showed these results at Ramanujan first letter page number entry number 7, where Ramanujan wrote the coefficient of x power n on some series, right, involving hyperbolic cosine function and sine function. That actually indicates that Ramanujan had the idea of partitions. Okay, so these are actually coming from that. But unfortunately, Hardy was an analyst, so Hardy was not interested in the general formula. Hardy was interested in the asymptotic formula. So Hardy forced Ramanujan to write down the asymptotic formula, which is kind of very absurd. But anyway, instead of finding the actual formula, Ramanujan and Hardy published a paper in 1980, which is this formula. There is a background noise. Is there everything fine?
Gagan, close your mic.
Yeah, so some big background noise is there. Okay, so this is the famous formula, asymptotic formula of Hardy and Ramanujan. The partition function is asymptotic to exponent of pi root over 2 n by 3 divided by 4 n by root 3 in tends to infinity. And obviously, Hardy was more interested to find out asymptotic formula because he was an analyst, right? But Ramanujan is number theory, he wants to find out the actual formula, like correct formula. But because Hardy was the mentor, so he could not write down that thing. Later, obviously, Selbach wrote. I mean, I don't have time, but I can tell you the story of Selbach later, maybe another day. Okay, but later in 1936, actually, another famous mathematician, Hans Rademacher, he gave the actual formula, and you see that this formula, Rademacher formula, actually involved these hyperbolic functions, and he also got in idea from this Ramanujan notebook. So you understood that actually it could have been by Ramanujan itself, but unfortunately he could not get the proper guidance. So finally ended up with the asymptotic formula. But anyway, so the partition function, what is important? The formula is not so important. The important is the method. The method here, which Ramanujan introduced, which calls the circle method. And the circle method actually changed the course of 20th century mathematics. So this is the so impactful method. Unfortunately, people call it Hardy-Littlewood method. But I condemn it actually. I feel that it should be called Ramanujan-Hardy method rather than Hardy-Littlewood method. Because Ramanujan had this idea to his notebook. Then Hardy realized later, and then Hardy has more work with Littlewood later, obviously. So this method was called on 2 lines. What is the application of this method? The circle method is actually summing of the value of infinite sums on infinite circle for each rational points, and the sum for this infinite sum has a main term which coming from the rational points, and the error terms coming from the rational points. So this idea is completely genius idea of Ramanujan. Obviously, Hardy actually polished the idea of Ramanujan. There is no doubt about it. And then it has lots of application. For example, one of the most interesting problems is called worrying problems. So worrying problem is first actually known by Gauss itself. Gauss first proved that every natural number can be written sum of 4 squares. Probably you may have heard this theorem. Every natural number is a sum of 4 squares. But then people ask, you cannot do it by less than 4 numbers. So you cannot write down every natural number by sum of 3 square. Okay. But the question is that what about the higher power? Can you do it instead of square? If I write down by cube, then how many numbers we require? Or for for 4 power or whatever. So these problems are called wiring problems. The wiring actually investigate those problems. And the main tools to prove this kind of formula is actually circle method, the method which Ramanujan invented in 1918. The paper was published in 1918. And you will be probably happy to know that the most difficult case was the case to find out G4, which is 19 actually. That every integer can be written as sum of 4th power by 19 integers. And this is due to joint work with the Indian mathematician R. Balasubramaniam, my former director at my place Institute of Mathematical Sciences, with French mathematician Desuet, Professor Desuet, and Balasubramaniam, and one more person actually. So Indian mathematician also involving this great kind of work. Okay, this is one. Another one I should say, that is called Goldbach Conjecture. What does Goldbach Conjecture say? It said that every even number can be written as a sum of 2 primes. I mean, every even number means even number bigger than, I think, some stage they say. Okay, bigger number 2 probably. For example, if you write down 6, you can write down 3 plus 3. If you take 10, you can write down 3 plus 7. You can write down 5 plus 5. It's not unique, obviously. There may be more than one. So these problems that are called Goldbach Conjecture, this is still open, but there was a odd version of this conjecture that said that every odd number can be written as sum of 3 primes. That is called ternary Goldbach Conjecture. And for special cases, this is known due to many work of Bombieri and other. Bombieri is also a field medalist, a mathematician. And what is the method? Method is again the Ramanujan method, and there are many, obviously, in the modern day something called shift theory, but the idea is again that circle method of Ramanujan. Okay, so this is it's worrying. This is Goldbach, and then what is the impact on? Okay, so this is one more influence of number theory is called probabilistic number theory, and this is also obviously came from another very famous paper of Hardy and Ramanujan, and what they find out something called normal method. So briefly telling that if you have a natural number and if you want to know how many distinct prime factors are there, these numbers are called little omega, and then they prove that this is actually of the order of log n. So those numbers whose number of prime factor bigger than log n is very negligible. So the limit in x divided by x tends to 0 as x tends to infinity. This is also one of the most influential work of Ramanujan, which actually started the new area of mathematics called probabilistic number theory. Okay. Then obviously it has a famous result later that I am not going to discuss. Now let me tell you another very nice story. Before that, let me tell you Ramanujan illness. Okay, so what happened? Let me tell you the story when Ramanujan came to England, 1914. Within few months, the First World War started. Probably we know all of us knows the First World War was there from 1914 to 1918, and British government forced almost every capable human to go to the battlefield. You will be surprised to know that even Little Wood was sent to battlefield as a position of captain and then later major probably. Yes. Okay, so fortunately Hardy was the person who did not get the call letter from British Army to join Army. Okay, so this was Hardy was very lucky. And that is the time during 14 to 17 Ramanujan and Hardy has peaceful work, because the world was going outside, so they can do work inside. But unfortunately, because of the world war, almost all the farming thing was done. Like there was no farming procedure. Like all the farmers was going to battle, everything, right? So the main source of food was the meat from chicken, meat from beef, ham. These are the main source of food. And because Ramanujan was a Brahmin family, he was a like vegetarian, complete vegetarian. So he was he did not even take those kind of foods because he did not. First of all, this is not his diet, and second thing is that he's a completely vegetarian. And on the other hand, the vegetable was also not available. Like he used to get sometimes with bread, sometimes some vegetable once upon a time. And most of the time, he was starving. Ramanujan was starving at Cambridge with that much temperature, cold temperature, without food, and doing and solving all these big theorems, all this work. So you can understand that can you survive almost 3 years or 4 years or till before he fall ill, almost 4 years he survived almost without food, and proving you will be surprised to know that in this short span he wrote 30 papers which are all very, very good standard papers. Okay, almost 30 papers. Before going to London, Cambridge, he wrote many papers, like around 10, 11 papers. But most of his 30 important paper was during this time. And he did all those things when the First World War was going on without food. Remember this thing. On the other hand, Hardy used to have enjoy good meal because obviously he's not a vegetarian. And this leads Ramanujan to the illness. Okay, so he started this tuberculosis, which is called TB nowadays. So finally, he was moved to the sanatorium, and he was sick after probably at the end of 17 to 18, and then finally 19. The situation was very, very bad. So Hardy and they moved him to the sanatorium after the end of First World War. Okay, so now the most famous incident happened, which all of us knows. In fact, this is the incident which actually I learned from that book in my childhood school, and that is the number 1729. This is the story. So what happened that one day, like other days, Hardy came to meet Ramanujan. Okay, and he came to meet Ramanujan with a taxi, and Hardy used to crack a joke. So he cracked a joke that this is you can see that taxi. So Hardy cracked a jokes that I just came with a taxi number 1729, which looks like a dull number to me. I hope it is not a bad omen. And then this is the famous reply of Ramanujan. Ramanujan replied that on the contrary, this is a very interesting number. It is the smallest number that can be written as a sum of two cubes in two different ways. And this is the implementation. Yeah, so before that, yeah. So you can write down this is 1 cube plus 12 cube or 9 cube plus 10 cube. And there is no number smaller than 1729 which can be written as sum of two cubes in two different ways. Okay, so you understand that, I mean, how much he played with numbers that you are getting this much result instantly. Okay, and there are many such numbers actually, and later obviously generalized to call, nowadays this is called taxicab number, and Ramanujan number is called the second taxicab number. Okay, obviously the first taxicab number was 1 you can write down 1 cube plus 1 cube, and so the third taxicab number is like this 8753331. This is due to Leach, and you can write down this is the smallest number which can be written as sum of cubes by three different ways. 163 7 cube plus 436 cube. Again you can write down 228 cube plus 423 cube. Again you can write down 255 cube plus 415 cube. Similarly, fourth taxicab number and other thing is also in literature. Till I think 5 or 6 is known. For 7 it is not known. They have some bound. Okay. Okay, so this is just a brief story. Obviously this is not known for large number. This is also open problems. Yeah, so what happened after this incident, and Ramanujan was little bit better, and then he was sent back to India in 1919, and within few months in early 1920 he was in bed in Kumbhakonam deathbed, but he did not stop doing mathematics. This is the most important thing, and he wrote a letter on 12 January 1920 to Ramanujan, and he said that this he wrote to Hardy that yesterday night Devi Namagiri came to my dream and he gave me he told me that this mathematics, new kind of mathematics is linked with the existence of world and other things. Okay, and I was thinking these problems, and the goddess Namagiri, he was kind enough to show me the path to work with this kind of problems. Okay, so I am not saying the wrong or right thing. Generally, in Indians have this habit. Whenever we cannot actually explain something, we say this must be act of God. For example, if something happened, we said that Bhagwan ne kiya hai, or this is Bhagwan ka kaam, something like that. Okay, so I think Ramanujan also was a devotee of this Namagiri, that goddess Lakshmi. So probably that was going through his mind. I don't know actually what happened, but then he wrote to Hardy about his new invention, new discoveries, these mock theta functions. Later, actually, people realized that these are very special case of something called nowadays mock modular forms. And you will be surprised enough that these mock modular forms are actually involved with the existence of universe, in particular black holes and wormholes. And this work was due to Ken Ono, which I told in the beginning, the name. Okay, so this Ramanujan's last letter actually shape now the 21st century mathematics to the so that people can understand the idea of mock theta functions and probably the application of those to the existence of black holes, wormholes, and probably the creation of universe. So nobody knows actually what is the ultimate application of those theoretical problems. So this is, I also believe that whenever somebody is proving a theorem, many people ask that what is the application? What is the application? But I believe that you don't have to think about the application. Okay, you do your work. The application may come after 100 years. Okay, so it happened several times in the history of literature, in the history of science, that people did something and after 200 years, people have find out beautiful applications. Okay, so same thing happened with Ramanujan itself. And with this, probably I will stop. My lecture is quite big, and I thank all of you for your patience and listening to me. And please feel free to ask me questions.
So if there is any query, then you can ask. Yes, participant.
I'm getting one important call. Yes, please feel free to ask me question.
Sir, in the Goldbach Conjecture, you have said that every even number can be written as sum of two primes.
Yes.
So, how can we write 3 as a sum of two primes?
3 is not an even number.
So, 2 as a sum of two primes.
I said after 4. You missed
Okay,
my
sir.
point.
Okay,
And
sir,
this conjecture is still unknown. This is not, there is no proof yet. Saksam, you can try to give a proof, and trust me, you will get a Fields medal.
Okay, sir. I will surely try it.
Yeah, please try.
Okay, so if there is no other query, then thank you very much, sir, for giving an enlightening talk. We are grateful for the time and effort you took to share your thoughts with us. Thank you once again.
Okay.
Now I invite Dr. Harmanpreet Singh Kapoor to present the vote of thanks.
So good evening, everyone. It is my privilege to have been asked to propose a vote of thanks on this occasion. I am Dr. Harmanpreet Singh Kapoor. and on the behalf of Department of Mathematics and Statistics, Central University Punjab, I'm here to present the vote of thanks for today's webinar. First of all, my sincere thanks to Almighty God for making today's event a grand success. On behalf of Central University Punjab, I would like to thank our today's speaker, Dr. Tapas Chatterjee, Assistant Professor, Department of Mathematics, IIT Ropar, for enlightening us with this knowledge. Today's webinar was full of knowledge and interesting thing. It gave deep insight into or also revealed some interesting fact about the life of Shinyuasan Ramanujan. I am pretty sure the precious knowledge that Dr. Tapas Chatterjee gave will definitely help students in their studies and research. Once again, I would like to thank Dr. Tapas Chatterjee for taking out time from his busy schedule and enlightening us with the knowledge. I also would like to thank our Honorable Vice Chancellor, Professor Raghuvinder P. Tiwari ji, for motivating us. I would like to thank Professor Ramakrishna Vasurika, Dean in charge academics, for motivating us to organize this webinar session. I also want to thank all the faculty members of the Department of Mathematics and Statistics who really work hard to make this event successful. Also, thanks to all students or participants for paying your attention. Once again, I want to thank we are grateful to Dr. Tapas Chatterjee for being with us. Thank you very much, sir.
Thank you for the opportunity to speak here.
Over to you, ma'am.
Thank you very much, sir. Now I request you all to please stand up for national anthem. For your active participation in this event. Thank you.
Okay. So now may I take a leave, sir?
Yes, sir. Yes, sir, you can.
Okay. Thank you, everyone.
It's a matter of great honor and pleasure to appreciate and reward the hard work of the students, hence to acknowledge the talent and creativity of the position holders. It's time for the prize distribution ceremony. The results have already been prepared by our jury members. It was a really a tough call to decide the winner. I now request our judges to please come on the dais and honor the winners.
Certificates. ये क्या है? मैम आप पहले पोस्ट कर सर्टिफिकेट को भी नाम के अकॉर्डिंग पोस्टर में पहले स्पीच होएगी
Let's start with the result for Rangoli competition. The second prize for the Rangoli competition goes to Miss Jyoti Kumari. Jyoti Kumari and Mr. Ravindra Yadav. Please put your hands together and say thanks. And the first position holder for Rangoli competition is Team A, Miss Payal, Miss Neetu. Please come on the stage. Now, next are the results for speech competition. The second position holder for speech.
third.
The third prize for the speech competition goes to Mr. Satya. Now it's time for second position. The second position holder for speech competition is Mr. Shivan Pal. Now, the first prize for speech competition goes to Miss Harmanpreet Kaur. Now, last but not the least, winners for the poster presentations are the second prize for the poster presentation goes to Team C, second position. Also, the team D is the second position holder. Miss Simmerpreet Kaur, please come here.
ये है ना ये सॉन्ग
The first position holder for the poster making competition is Team A, Mr. Saurabh Kumar and Mr. Shwan Pal. Now I would like to call all the participants, Miss Manorama and Miss Jaspreet.
इसको बैठने पर करने से मैं सबको भी दे देना वो तो वैसे भी किस चीज में है जैसे की पोजीशन में है मैं बुलाना फोटो वैसे फोटो उन्होंने दूसरा किसी और ने बोला था सॉन्ग था इसका इनको सॉन्ग के लिए दे दिया था इनको पोस्टर के लिए दिया आप भी ये पोस्टर के लिए दिया सॉन्ग के लिए दिया बस हो गया
Congratulations to all the participants.
सभी को दे मैं ये जो पार्टिसिपेट किया है
सभी लोगों को बहुत बहुत बधाई। आप लोगों की मेहनत, क्योंकि ये प्रोग्राम तभी सफल हो पाता है जब आप लोगों का सहयोग हो। Once again, a lot of thanks to all of you. And I hope that next event, which we will organize, is likely to be this year 5 days. So that will be, I think, इससे better होगा I hope. Okay, so thank you.
सर ये जो सभी पार्टिसिपेंट ऐसे दे दें हम आपको समझा रहे हैं विनर्स की लिस्ट
एक फाइनल लिस्ट बनाई है आपने, फाइनल लिस्ट दे दीजिए ना।
फोटो ले